Good morning. Welcome to this session on commercial Earth observation data and services for urban context. Very nice to see you all in the room, and maybe there will be some more coming also in the next minutes. I know it's a bit of a difficult organizational setup between moving around between the rooms. My name is Peggy Fischer. I'm the third-party mission manager at ESA, and I'm also responsible for the Copernicus contributing missions. And I'm very happy that our colleagues, our ESA colleagues that are organizing the URBIS workshop have given us an opportunity today to organize this session, which is going to be about commercial Earth observation data in the urban context. We have invited 4 companies to join us today in this session. There will be SatView, there will be Constellar, Egeos, and also Prometheus Intelligence presenting after me. I will give you an introductory session about our ESA activities in terms of procuring Earth observation data from commercial data providers. And this session I'm also co-chairing with my colleague Romain Estève. He is a space economist, and he's working as a Copernicus contributing coordinator in the ESA CCM team. And we will be guiding you together through this session today. So if someone could load up my presentation. Okay. So let's go to the first slide. Yes. Let me illustrate to you an overview on what is happening in the ESA Earth Observation Directorate in terms of procuring commercial Earth observation data. We are actually procuring data and associated services for our own purposes, of course, in ESA, but also for other institutions, primarily for the European Commission in the context of Copernicus. So there are 2 main elements, the third-party missions and the Copernicus contributing missions. In the first part of the presentation, I will go into more details on the ESA TPMs, and then later on also we'll talk about the Copernicus contributing missions. On ESA side, we are procuring commercial data primarily in order to sponsor it to projects, to research projects, science projects in ESA member states in Europe. And this is very much appreciated by everybody. And we are also taking a lot of care on data quality aspects. So there is also an expert team on ESA side working on assessing the quality of, in particular, commercial data before we are distributing the data to the scientific projects for their use. And in this context, we are also collaborating with NASA, as they have, you might know, a similar program ongoing in order to procure commercial data. Much bigger budget than ours, but very similar, and we are collaborating jointly. And in the context of Copernicus contributing missions, here, the purpose of the data purchase is for purely operational needs. So it is important to understand the difference here, that in Copernicus, as you know, the Copernicus services are producing operationally products, and they need this commercial data to flow into their production chains as rapid as possible. And here there are stringent requirements to deliver the data. In the context of Copernicus also, we are engaging, or we have engaged with many data suppliers. I will show you a little bit more about that later on, but there is a collaboration ongoing with what we call established data providers and also emerging data providers in Europe. And there are 2 companies today that will present, Constellar and also Prometheus, that are in part of this category of emerging European data suppliers in Copernicus. Now, the ESA third-party mission scheme is really a central component in ESA, in the Earth Observation Directorate. So what are the ESA third-party missions? These are all non-ESA missions. They are not owned by ESA, they are not operated by ESA, but we have arrangements with these data providers to promote their data and to deliver the data to different science teams and researchers, and also to incubation activities that ESA is following as well. There are many missions in the portfolio today. There are over 50 missions there, and even more instruments. And there are different data domains. I invite you to go to the website in order to go into more details of the portfolio and how you can access also the data. Important is that, of course, in many of the projects, commercial data is used in combination with other data sets. So the Sentinel observations, free and open, or also Earth Explorer missions, ESA Earth Explorer missions, and any other national or scientific missions. So there is a lot of benefit if data sets are joined together, and we are very happy at ESA to contribute to many scientific advancements, providing this commercial data to the scientists. This infographic shows the evolution of the ESA TPMs over time. You can see that in the last years we have been very active in onboarding additional missions, and primarily commercial missions in different domains. So you see atmospheric composition data, SAR data, optical data, but we also have radio occultation data now from SPIRE, and we are working with radio frequency data, in particular unseen labs for the moment. And we are also engaging with thermal infrared data providers, SatView, for example, but also in the future with others. We would like to include also high-resolution thermal infrared data into the portfolio in the near future. So now the next slides aim to give you an overview of the type of applications that can be covered by, with the use of commercial Earth observation data. So I aim to show you a bit an overview of applications. It might not be completely complete. There are some missing elements potentially, but it gives an overview, and it also aims to indicate the type of data that can be used for applications. Again, all the information about our TPM offer is available on the ESA Earth Online websites. So at high level, you can see that we have put here the data offer, which is mostly used for urban monitoring, for urban pollution detection, sustainability and development, for mapping, for heat maps, hazards and risk detection, and also flood extent monitoring. But again, there are other applications possible, of course. The next slide is showing you again, also the type of data we have been giving to the different research projects in the different domains that are aiming to monitor urban context. And since 2022, we have actually supplied data to over 80 research projects. In fact, they all have shown us results, and we're also publishing success stories about the results of these projects. I will get to that a bit later. Again, you can see here the different types of applications that have been surveyed in these projects. Urban pollution detection, for instance, sustainability and development, with green spaces and biodiversity. Also various projects on urban mapping related to infrastructures or hydrological impact. Heat maps have been generated. And also hazard and risk detection was done in the context of natural disaster monitoring and various other activities. Now I will run you through a few slides that go into more details on the data offer in TPM in particular. I'm starting with the very high resolution optical data which we have. So here you see a few examples of the data that is available. Vision 1, for example, or GeoSat-2, and also models that can be generated out of very high resolution optical data, and applications primarily for optical data, urban planning and land use analysis, infrastructure monitoring, the 3D modeling of cities, also smart city planning and development, change detection for construction, identifying legal construction, and many more use cases. I'm sure you have heard also very interesting information yesterday already in the workshop about these applications. Then I would like to draw your attention to one specific project which was also in the context of urban monitoring, WorldStrat. It was a project followed by our colleagues in the Phi Lab, at the ESA Phi Lab, and here also the TPM team contributed with very high resolution optical data in order to allow for the generation of an open source data set of high resolution imagery that can be used for machine learning methods, and it combines over 10,000 square kilometer free high resolution data, and it also covers various cities and different urbanization densities. It was generated out of Spot 6 and Spot 7 data, plus, of course, lower resolution data, Sentinel-2 in particular. Then I would also like to mention that there's also the possibility to gain access to what we call super high resolution optical data, so where, for instance, a Pléiade Neo 30 centimeter native imagery can be further modulated into even 50 centimeters, so there are, you know for sure, algorithms that can be used to enhance the level of detail in the imagery by still maintaining the native ground sampling distance, and this allows smaller objects to be detected in the image without affecting the geolocation accuracy. There is also this article on that slide which gives a more comprehensive overview on the different super resolution data sets we have. It's not just Pléiade Neo, there are more, so you can go there if you like for more details. Then we have also SAR data, very high resolution SAR data in the portfolio. Here you have some examples, ICE-I and TerraSAR X. We also will have a presentation later on about Cosmos SkyMet. And also SAR data is very much used in the urban context, can be used for flood monitoring in urban areas, urban development, but also ground deformation analysis, infrastructure stability, and so on. Flood analysis, there are various applications, and I'm sure also there were talks already yesterday about these topics. Then I have one slide about atmospheric composition data and how this can be used for urban monitoring. So here, colleagues have used both Sentinel-5P data and GHGSAT data to monitor the emissions over landfills close to Madrid. And in fact, it shows a very nice, illustrates very nicely how Sentinel observations can be combined with commercial data to achieve very good results. Then I would like to remind you that we have also now a sample data gallery online available, so there are from various missions sample data sets available that you can trial out before maybe submitting to us a request for the data. So you can have a look at that. We can also populate it with more information if there is something missing. I will not go to the details, but it is required to submit to us a project proposal to gain access to commercial data. There is also a link here to an article that illustrates the various steps and brings you to the different steps that need to be done. There is an online form to be filled in for the moment and for us to then evaluate your request and allow you to provide the data. Then we also have a TPM data access guide online where you can find all this information. It's a very comprehensive document, and we also have the link here to the TPM terms and conditions. Important that you are aware of those as well, that really the TPM data can be used for scientific purposes, research, and for incubation activities, but not for commercial activities. We are very keen in publishing regularly success stories about the use of commercial TPM data or also other TPM data. So if you have results, if you like to have a joint publication with ESA on your results, please reach out to our editorial team and they would be very happy to engage with you on working in generating an article, and then we would promote this on our ESA communication channels. And then I would like to wrap up the presentation about the Copernicus contributing missions. So this is our current portfolio of Copernicus contributing missions. You see the established providers, and you see on the right side the emerging European Copernicus contributing missions. We have placed 9 contracts in 2023 with 9 companies. You see them here. And we are working now in the 2nd year, and there's a lot of progress, a lot of interaction with these companies happening. The main goal on ESA side, and you see also the companies here again on this infographic, is to support them in, or guide them to the extent possible on data quality aspects, on CalVal, and in terms of fine-tuning the data they are producing from their space segment. And there are expert teams following these companies now, and we are also engaging with the Copernicus services. We are we are in dialogue with the Copernicus services and the companies to illustrate the new data offer, the new capabilities that Copernicus could have in using this data. In particular, also because we have new domains here in the portfolio, thermal infrared data, hyperspectral data, and also atmospheric composition data, which up to now on a commercial side wasn't really used in the Copernicus program. So there are a lot of opportunities here, and we are working a lot with the companies and the Copernicus users. Again, one slide about the Copernicus context. So there are 6 Copernicus services in place today, as you know, and we are delivering in the ESA service to most of these Copernicus service commercial data. So ESA is actually the entrusted entity of the Copernicus contributing mission activity as an implementer. The program manager is the European Commission, and the European Commission is also funding all the activities. But we are implementing the activities, we are placing the contracts, and we are managing the service also to providing the data to the Copernicus users. We have been working a lot with the European Commission on a new also policy in terms of data buy, where we are giving preference whenever possible to European data providers. Therefore, also this push to bring European emerging data providers in. But of course, we're also procuring still data from what we call non-European satellites, in particular in optical very high resolution and other domains where there is not yet enough operational data available. And I mentioned that before, also in the Copernicus contributing mission context, ESA is taking care a lot about the data quality. And I think that's my last slide, just to remind you about this URBIS24 Workshop, which is coming up, which is a very important forum for all commercial data providers, ESA, Copernicus services, end users, to talk about data quality and Calval procedures and various other topics, analysis-ready data sets. If you go to the website, you will see all the different topics that will be addressed in this workshop, so I invite you to have a look. And I think also the abstract submission deadline is coming up now, so have a look if you would like to participate and register. Thank you. This is completing my presentation. If there are any questions, I have to take them if we have time, because now we need to go to the other presentations. Thank you. It would need to be seen in the details. It could be possible if you would be part of an ESA incubation activity. So if, I don't know, in terms of incubed activities or something related in a business incubation center of ESA, then it could be possible, but it would need to be seen in the details.
Thank you, Peggy. I'm going to call on stage for the first presentation of the second presentation after Peggy, Natalia Kuniewicz, who represents SATVU, and will talk about the innovative solutions for urban heat challenges and the insights provided from their first satellite, HotSat.
I think you can hear me now. Good morning, everyone. Thank you for your attention, and thank you to the organizers for inviting us to speak at the event. I'm Natalia Kuniewicz. I work as Business Development Lead at SATVU, a UK-based company that provides high-resolution thermal data from space. The company exists since 2016, but only last year we launched our first sensor into space. Unfortunately, it experienced an anomaly after 6 months of successful operations, which was a major setback, but which also allowed us to go through all of the acquisitions that we managed to capture within the 6 months and validate the commercial or other interests in the key verticals that we're trying to address with that novel technology. So one of them is obviously urban heat and the way it can be portrayed in 3.5 meter thermal data. After we released the first light images coming from HotSat-1, the first satellite, we were contacted by a number of city officials, data scientists, solution providers from all around the world, inquiring about the utility of our data related to the subject. We now know that issues that we can address or that we can inform people on mainly relate to public health, mortality, infrastructure risk, productivity loss, biodiversity impact, and others. I think you know better than me what are the applications or what are the research areas, given the extensive presentations that we were witnessing over the last 2 days. Just to explain to you where we sit on the electromagnetic spectrum, as HotSat satellites are equipped with a single band sensor, which observes or monitors the Earth in midwave infrared. It's quite new to the market. I spoke with a few solution providers who are experienced in midwave infrared imagery handling, but these type of data at this level of resolution usually came from drones or aerial surveys. It's quite unique that this solution will be available globally and in a very easy, approachable way. In the meantime, we saw so many developments in optical and SAR data recently in the last decades. It's only the right time for thermal to catch up. Our key differentiator is the fact that we observe at 3.5 meter resolution at nadir. We can monitor any area in the world every 3 to 5 days at day and night time. We also have a video capability. Our camera is a frame camera that can be off-pointed at 45 degrees. The video capability can indicate any movement, so we can see at what speed something is moving and in what direction it's moving. And it's a globally scalable data set. I think it speaks for itself, given the global problems of climate change that we're facing. A scene collected by HotSat satellite will cover around 16 square kilometers of land in real world, which is excluding us from certain applications, such as, for example, agriculture, where we know that the crops cover much more extensive type of swath. But on the other hand, monitoring activity in buildings or monitoring heat distribution in a city is the perfect fit for that scene size. As I explained, it would be a midwave infrared type of data with the frequency of revisits every 3 to 5 days. Despite the setback that we experienced, we are still fully funded to launch the next 2 sensors. This is happening in 2025. I think the precise timelines will be announced very soon. And we're striving for a satellite constellation of around 10 satellites. This is a timeline that really irons out our activities up to date. Last year, we were quite successfully serving the first customers, and we're on track to launch the next HotSat-2. Given what I said about the application of urban heat, I think some of the research studies that we came across, or the typical experience of a midwave infrared user applying satellite data relates to Landsat imagery. This is an example that refers to that 100-meter resolution image, and this is the same location that is covered with 3.5-meter HotSat image. We can quite clearly see that there is the cooling effect provided by the greener areas on the right-hand side of the image, and that extreme heat signature coming from the street. This is another image collected from Rome. That's a nod to the organizers, but also a very good example of how precise insights from that type of data can be. We are observing 2 very popular touristic attractions. One is Vatican City, and the other one would be Castel Sant'Angelo. One is lined with trees that are providing a shading effect. Another one is fully deprived of any nature. So even if we zoom in at that scale, we can pinpoint the hottest or the coldest areas in the city. Another example coming from Fresno in California, interestingly, the area that we can see in the very middle of the image is populated by more wealthy communities in the city. So building a timeline of heat signature and heat distribution across the city can very easily be embedded in that socio-demographic context of a city and prove the best results for the most efficient policies given both heat distribution but also who lives there and who is affected by these extreme heat events. And finally, a solution that was proposed by one of our partners, the Office of Planetary Observations that are based in Australia. They benefited from a few coverages of key Australian cities. They work directly with private healthcare, but also local authorities. The solution that they propose to their clients takes the context-aware heat stress areas, the maps on using the land cover, but also canopy cover percentage and tree stress index. They would normally inform that with downsampled 10-meter, 30-meter thermal resolution. They were very happy to ingest 3.5-meter thermal image, and the solution indicates where planting trees will be most beneficial. So yeah, it's a very simple way of integrating Earth observation data into policy decisions and budget distribution. I will now mention a few product information. Despite the setback related to HotSat1, we have been working on the improvement of both our platform but also the data product levels. So at the moment, what is available to users is a visual image that comes in a very simple, easily integratable format as GeoTIFFs, which can be opened with freely available software such as QGIS. It's a one-band thermal brightness image. We have a platform through which we deliver this data. At the moment, we have a few hundreds of images that can be browsed through the platform. In the meantime, we're also improving the processing of the imagery. So here, we would love to hear from users who are experienced or are planning to build solutions and engage in programs that would benefit from thermal imagery in the future. So far, the visual product was an intuitive tool that can help differentiate between the cold and the warm features of a scene. We're planning to improve to the level of land surface temperature, but that requires further work. At the moment, we're prototyping brightness temperature products at both top of atmosphere and bottom of atmosphere level. And that's a glimpse into our platform. In the future, users will be able to task the satellite as they wish, and the platform is quite intuitive to use. We're also an API-first company, so demanding both catalog and fresh data will be available through API and through a browser. So if you have any ideas about projects that our data can inform, please get in touch with me. I'll be happy to have a discussion about that. And yeah, I'm hoping to see more insightful publications and research studies that we can support. Thank you very much.
Thank you, Natalia. Perfectly on time. So we have a bit of time for a few questions, if you want. And we have microphones for you.
Hi. First of all, thank you for this very nice presentation. And I was wondering if you could elaborate a bit on whether and how you perform some correction for directional effects in your imagery.
Sorry, which effects are you asking about?
Directional effects.
Dimensional effects.
Directional.
Unfortunately, I don't think I can answer this question. I'm not a technical member of the team, but I'm happy to get back to you when I do get information from my technical team. What I can tell you is our data is, as a standard product, is geo-referenced to about 30-meter accuracy. that's the quality that we commit to. Yeah.
Okay, thank you.
Thank you.
Thank you for your presentation. I had a question about, you talked about the spatial accuracy, but do you also have something to say about like the thermal accuracy?
What we know is that our sensor is sensitive to 2 degrees at the sensor level. So this would be the best indication of the thermal sensitivity.
We have one in the back.
Hi, and thank you for a great presentation. Just really quick, what's the price?
That's a very good question. We operate on a pay-per-image business model. So there is a set price for our imagery. Us being here and being invited by ESA, I think is a sign that the data is going to be requested by the audience, by the TMP users in the future, which is a great indication. I'm happy you're asking about it. As a commercial provider, we're also trying to make to be as flexible as possible. So I think once we know the project, we can dive more into the details on adjusting the pricing. It's not, from what I've heard so far, it's not anything extreme as compared to other commercial providers. But we'll be doing our best to adjust to the needs.
All right, thank you.
Thank you.
If I may just add to this, if we have a successful conclusion on, for instance, access to some of the 6 months archive of HotSat1, of course, this would be free of charge for scientific users. Again, the project proposal would need to be submitted, but in the context of TPM, we would be able to sponsor this data.
Thank you.
Who goes first?
Very quick. Thank you also, Natalie. My question is if you have already selected specific Calval sites for this HotSat2.
No, we haven't. And I would be very happy to hear of any interesting sites to monitor in that phase, both in the commissioning phase, but also later.
Yeah. I have some suggestions, so let's talk later.
Perfect.
Thank you.
Yes, let's connect.
One last question.
Damien Ruban from Work from Space. I'd like to ask about the accessibility of new task data, because as far as I understood, right now you can access only the HotSat1 archive because of the failure. And then what is the timely schedule for the HotSat2 to get to be launched? You said 2025. Can you be more specific? Like
Yeah,
if you want to
definitely.
task it in the future?
Yes, so we're planning a launch in summer 2025. After about 3 months of commissioning, data will be available, and the next satellite is following suit. So after a few months, we're awaiting the launch of the next satellite.
Thank you.
Yeah, thank you very much. Thank you.
Thank you, Natalia.
Then we invite the next speaker to come forward, which is Tobias Leismann from Constellar, and he will give us insights into Constellar Hive thermal infrared satellite constellation and how the high-resolution land surface temperature can be used for urban infrastructure monitoring.
Thank you very much, Peggy. Hello, everyone. I'll just jump right in. So we're staying with thermal as SatView, only we are going for long-wave infrared, not mid-wave infrared. And so Constellar was founded in 2020. Research started earlier, 2016, at the Research Institute, and then we spun out of that Research Institute. And we designed a constellation of, this is not by accident, 5 satellites in the beginning for especially looking at agriculture, environmental monitoring, and heat resilience. And the same as SatView, we did have a lot of interest in urban monitoring as well, especially urban heat, so the health issue, urban heat island effect, but also urban greens, the health of urban greens, urban infrastructure, like what's the health of the roads and the tracks, and also energy efficiency, both cooling and heating has been asked of us. As you can see here, five long-wave infrared satellites, beautiful, right? So we finished building the first one. I'll show you an image later. Actually, I just came here to show you the image of the satellite. And we'll have a second satellite in construction right now. A third satellite is already financed, so we are good to go. Let me come here. So thermal is very needed, right? It's very interested. It's an essential variable for climate change. And so far, the remote sensing long-wave infrared thermal world is either you have higher resolution or you have higher visit time. And there will be future missions in the corner of high visit time and high resolution. And of course, there will be the Copernicus expansion mission, LSTM, there's SPG in the US and Trishna. And we are going here, like we have a 30-meter resolution at a daily visit time. And that means going from this image, from Sentinel-3, we want to go here, right? So you see a lot of more detail. And actually, this is a Landsat-based acquisition and using our processing. And the same as in the image of Satvu, you can already see where the wealthy people and the non-so-wealthy people live, because it's cooler where the wealthy people live, because they have more water and they can cool the area. So how are we doing this? We fly a satellite with a cryo-cooled detector, long-wave infrared. We have 4 bands. If you come to me later, I can give you all the details. I didn't put all the details on the slide. 4 bands in long-wave infrared between 8 and 12 microns, and we also fly a Vis-Near camera, which has the first 10 bands of Sentinel-2. So we have, at the same time, a 10-meter visible near-infrared and a 30-meter thermal acquisition immediately. We use the visible near-infrared, of course, for georeferencing our images, so they are exactly georeferenced to Sentinel-2. And we also use it for our atmospheric correction. We are aiming for an accuracy at nadir of 1.5K. We are able to task our satellite to plus minus 30 degrees, so with a swath of 18.5 kilometers, we'll be able to have a field of regard of, I think, 600 kilometers. Oh yeah, of course, it's a sun-synchronous orbit, and the first satellite will not be in our preferred orbit of 1 p.m., it will be in the 11 a.m. orbit. But the second satellite and all subsequent ones should be in the 1 p.m. orbit. Jumping from here to there, so satellite 1 is actually called SkyB1. So our first Hive satellite is finished, and on the bottom image you can see the 2 payloads. So the big lens, which is covered by plastic, of course, is the thermal lens, and the smaller lens is the visible near-infrared one. And the hardware is really finished and tested and everything, and the launch was scheduled by end of October, but it has been delayed. So we have done our part, everything quality checked, everything fine, and we're just waiting for SpaceX to get their act together. And it will be sometime end of year, beginning of next year. And not only the hardware is finished, also one word about processing pipeline. So we do have a very sophisticated processing team. We are also doing a lot for calibration and validation, working together with the Trishna and the LSTM teams. And on the left, so what we're doing right now is we're testing our processing pipeline with the available data from Landsat, from EcoStress, and all the others. And I just put one image here. On the left is the level 2 LST product by Landsat. On the right is our own LST product using the low-level Landsat data. This is because we use a much higher resolved emissivity layer in this case to be able to make it more usable. So if you have less artifacts and less holes in your data, it can be made more usable especially for users in the agricultural domain who have no experience with remote sensing, but need temperature data. So now I've brought 2 urban use cases, 2 different ones. to talk about, which so it's not a deep scientific work as most of the things we have seen in the last weeks, because we are a commercial company, but still. We have been working with, actually it's the University of Freiburg and the Karlsruhe Institute of Technology to source here Ferdinand Briegel, who did his PhD in building a universal thermal climate index model at 1 meter resolution, and we compared that to LST. And also used his model to use LST as an input data to see how far we can get without locally measured values. And looking for the idea, how is LST a scalable predictor for thermal comfort? And surprise, in some areas, yes, it works, in some it doesn't. On the left, you can see it's the old town of the city of Freiburg, right? I live there, so it's really nice. Not because I live there because it's nice. And of course, in the old town, you have shadows. So outdoor thermal comfort at 11 in the morning in the shadow is nice, while the Landsat acquisitions in the city center, of course, is dominated by the roofs. It has a 100-meter thermal sensor, so you don't see anything of the thermal comfort between the houses. This is going to get better if we have our 30-meter resolution, I guess much better. And the other thing you can see, the blue areas are open, non-sealed areas, so meadows and so on. And of course, if they have enough water, LST will be much lower than the thermal comfort, which is dominated by the sun radiation coming to your body. So yes, in this case, we can use LST for comparing the thermal comfort very quickly, and you can measure it remotely in a matter of seconds without using a complicated model, but it's not perfect in this case. But it will be better with higher resolution also for the city center. So in another thing, I didn't put a slide here. We also checked using LST as an input data, our LST for his neural network model, and it also predicted the same UTCI, so the thermal climate index, as the locally measured temperature. That was quite good, actually. Because if you don't need to measure locally, you can use it worldwide. It can scale. This is looking at the same kind of use case in a different way. So what we actually did here was just look at different areas, also again in the city of Freiburg, and using the effect. So if you have a piece of ground that has enough water and plants to cool itself, then usually the air temperature, the ambient temperature, and the land surface temperature will be in balance. You can see it here, I don't know, in the bottom right, you can see a part of the Black Forest. So this is 25 degrees at 11 in the morning at land surface temperature, and it's also the air temperature is 25 degrees. So that's fine. You can also see the lake and the urban forest, everything the same temperature as the air temperature. Then you go to the old town, you can see land surface temperature 45 degrees. Of course, the old town doesn't cool itself. But if you see in the bottom left, it says green city quarter. Actually, it's exactly where I live. So it's a very green quarter, so 50% of the ground is not covered by buildings and so on. And it was much cooler in the heat wave last year. And this is something that I think is easily usable even for people who have no idea about remote sensing. They can immediately see, if you have a normalized temperature, which part of the city and of the landscape is able to cool itself and which part isn't. And this has the beauty that you don't need a complicated index to look into, and you can get acquisitions really fast. Normally you have a local temperature. I also go in a little bit more detail here. So here we compared the 3 different points. So that is the green city living quarter, in the middle the old town, and then some part of the Black Forest, and looked at the different acquisitions over the heat wave in 2023 last summer. And as you can see in the bottom, the dotted lines are actually the air temperature, or always at 10:30 a.m. at the same areas. And you have the different LSTs values for in the city center on top. So the city center just never cooled itself. You can see on the bottom in the forest, in the mid of July, the forest was too dry. So the LST went up. So you could immediately see the trees were stressed compared to air temperature. And the middle line is the green city quarter, and you can see it's in between the forest and the city center, but still there was a spike in the mid of July because it was just too dry. So it nearly reached the LFT values of the city center. And with that, two things I come to an end. I only have this slide again. So for me, the conclusion is, yes, land surface temperature is essential. There's not much data available. We've already seen SATVU, we are here, and there will be more public mission coming in 5 to 7 years or so. We have seen that we can have a good correlation with UTCI, and even if you go higher resolution, it will certainly be better. And it is also nice to see that you can have a direct view of the city's cooling power and the stress plants with comparing it to the ambient temperature, and that's calculating a normalized temperature between LFT and the ambient temperature. Thank you.
Thank you very much for this very interesting presentation. We open the floor for questions.
Thank you, Tobias. Very nice presentation. I'm looking forward to the products. As I was wondering, probably I missed it, but I was wondering if you could tell us how many spectral bands are you using, and based on that, whether you are able to retrieve the surface emissivity or you use it from auxiliary product.
Okay. That's two questions in one, right? And the first question I can easily answer. So we do have 4 spectral bands in our LRISN there. That's between 8 and 12. I looked rightly before the presentation because I knew this question was coming, but I already forgot the exact numbers again. So please come later.
Yes, sure.
But it's 8, 9, 10.6, and 11.75, I think. And they are aligned to LSTM and mostly to Trishna. That was intentional to make it easy to use our data as a precursor for all the upcoming public missions. For the emissivity estimates, for urban, this is a very good question. We use our Visnir data for estimating the emissivity, which is optimized for agricultural applications and vegetation monitoring. For urban, we think we will be a little more off. And I'm looking forward to the presentation in the next session, who will talk about a better and emissivity layer, and maybe we can use that in the future. Okay,
thank you.
Thank you also, Tobias, for this nice presentation. At least you have Freiburg, which is an excellent testbed for the application with atmospheric measurements. So I have also a rather technical question, and the 1.5 degrees accuracy is impressive, and my question is if you have tested in the urban setting or in homogeneous non-urban setting.
So since the satellite isn't up yet, it's the thing we are aiming for, and it is for agriculture and at Nadir. So maybe at 30 degrees in the urban setting, we won't reach I guarantee you we won't reach 1.5 degrees, but it will still be quite good, I hope. Yeah. Yeah. I mean, many of the agricultural use cases actually depend on this accuracy, so we have been focusing very much on the temperature accuracy for agricultural use cases.
Hello, Renske Martijns, the City of Helsinki. I'm curious, do you plan to turn your data into very, let's say, practical, concrete tools and solutions or dashboards for cities as well? Or yeah, how are you planning to use your data in relation to cities?
That's a very brilliant idea. Let's build it together. Yes, of course, right now. So since we are a startup and we're launching 2 satellites next year and another one the year after, we are focusing on the data quality. But the idea of building dashboards or applications for different use cases has come up, and yes, for cities, it's on our agenda. But we actually do need some partners to do that. So we are willing to work together.
Maybe this is also a good moment to mention we have a large call for tenders coming up for exactly this kind of work, like cooperation between companies like yours and cities. So there's R&D funding up to 3 million. We will work with 20 different companies, cities of Helsinki, Amsterdam, Athens, Ghent, and Guimarães in the next couple of years. So anyone, you and any of your colleagues here, definitely Space for Cities is the project, and we very happily work with you.
Great, let's meet in the coffee break.
Thank you for the presentation. I'm also here on behalf of the city of Vienna, and I was wondering if it's possible to purchase the data you're testing with Landsat or EcoStress and your processing methods already, because
Yes.
we would need it quite urgently.
Yes, yes.
Okay.
Yes to all of it. Urgently, we are fast, and yes.
Okay, so I can just contact you?
Yes, thanks.
Thank you for the presentation. And my question is whether the data would have a global coverage, and what do you have planned also to do this global calibration, so that the accuracy for the globe would be
Yes, this is an
constant.
excellent question. Yes, there will be global coverage. We do have a lot of interest in Asia, in the US, and in Europe right now, commercial interest, and scientific interest also in other parts of Asia, in the tropics, and yeah, possibly tropical climate for calibration validation will be more difficult because there are no calibration sites. We are going, as I said, we are working with the Trishna team, who are also based in India, to hopefully share their data and our data, and we are already like in working terms with the French Trishna team to work on Calval. If you have more ideas, we are very open to do that. Another thing we are doing is we are trying to, or we are in the process of looking for own calibration sites and equipping them with a system that is mobile, so we could use it anywhere in the world and then do it again and again. And because we are very conscious that this is really, really important, especially for temperature values in different climates, different geographies.
Thank you.
You're welcome.
Thank you, Tobias. We'll move to the next presentation, but thank you very much for the presentation. I'm going to call now Axel Odone, who's going to present the Cosmos Climate capabilities and the unique capabilities for managing urban needs.
Hello, okay, good morning. I'm presenting the Cosmos Climate system. The Cosmos Climate system is a constellation of radar satellites owned by the Italian Space Agency, Italian Ministry of Defense, and has been produced by the Italian industry, Terrestrial Space and Terrespazio, and together with IGEOS we are running operations and commercializations. It's a constellation composed by 4 satellites of first generation, 3 are still operational after many years of activity, and the 2 satellites of new generation which were launched in 2019 and 25 that guarantee a program continuity to the system. 2 additional satellites for the second generation will be launched next year and in 2026, so that we have always at least 4 operational satellites, we hope more. All these satellites are on the same sun-synchronous orbit. This means that they have acquisitions over every part of the world in the morning and in the evening, so every 12 hours we have at least one acquisition, more acquisition with different geometries, so it's a revisit of 12 hours with the constellation. And of course, we have different imaging modes. As with all the SAR satellites, there are different capabilities. We go from the ScanSAR modes, which are very large swaths, typically with lower resolution, used to monitor large areas, especially on the sea. We have the strip map mode, which is on a 40-kilometer scene, available to monitor with 3-meter resolution. And then we have also the very high resolution, the spotlight modes, which are resolution 1 meter up to 0.3, 30 centimeter resolution. For each imaging mode, there is possible to select a different kind of polarization, different processing level, so there is the complete range of availability of options from a typical big radar provider. Of course, with the second generation, we had several improvements we have been made compared to the first generation. Of course, we had an increase in resolution, especially in the range direction through to a more powerful antenna. We have a better image quality, so less noise, and a better geolocation accuracy for the products, especially for the near real-time products, so the images which are immediately available have already a very good geolocation accuracy. And we have dual and quad pole possibilities, so it's like having 2 for acquisitions at the same price. Here you have an example of a picture of the Colosseum by combining 2 different polarizations to generate a color combination. What I would like to focus in this presentation is about the interferometric capability of the constellation. This is something which is typical from big systems which are able to guarantee an orbital stability, accuracy in time, and which allow us to take advantage of making acquisition with the same exact geometry, what is called interferometry. And having a stack of acquisitions with the same exact geometry allows to make very accurate analysis and comparison between different acquisition dates. Here you see how the satellites, the position of the satellites on the orbit allow us to take 5 acquisition with the current available satellites, 5 acquisition, interferometric acquisition every 16 days. So a single satellite repeats itself after 16 days. We have the possibility to make 5 interferometric acquisitions. A typical example of the use of an interferometric acquisition is what is called the multitemporal coherence analysis. So it is analysis between 2 acquisitions made in different dates, and which are put in the red and typically in red and green channel, and then in the blue channel we put the coherence between these 2 acquisitions. Here you see an example over a 40-kilometer area between Rome and the Fiumicino airport, and this is a very precise way to make a change detection analysis. Here in this example we have only 16 days interval between the 2 acquisitions, and if we zoom, for instance, over the area of the Fiumicino airport, we can clearly see the differences and what is not, what remains similar. So in blue is the coherent part. So typically the runways, the highway, everything which is man-made and stable, while vegetation and water are, by theory, incoherent, and so there are different colors, meaning the different kind of changes between the 2 acquisitions. And of course, in red and in green, you see the different, here are the planes that are on the different fingers that, of course, are changed between the 2 acquisitions. So this is an example of a very precise change detection analysis that you can make using interferometric acquisitions. What is very important to highlight is that since we are having a constellation which has been launched already in 2007, we have a huge archive of data. So we have more than 2 million acquisitions done in the last 17 years. And what is important is that we are monitoring very closely, using an interferometric capability, many targets worldwide. Here you have in this map an example of some of the targets which we are monitoring using interferometric capability. So we have a project over Italy. So there is a mapping of Italy, doing every 16 days a complete interferometric coverage of Italy. This is a project by the Italian Space Agency, Italian Civil Protection. But we have also different targets. You see all these dots are the major cities. So all the urban areas worldwide having more than 200,000 inhabitants are monitored since many years using interferometric acquisitions. Just to make an example here over the city of Istanbul, you see we have 4 different acquisitions that cover the city. The 2 central strips are started the acquisition in 2011, so we have more than 13 years of acquisition, having more than 200 scenes, so it's a very long history, and it's possible to make an analysis over these 13 years, a very precise analysis. The side strips has been added lately in 2023. You know, there are additional, the city is growing, so we are enlarging also the mapping, the interferometric mapping activity that we are doing. One of the other interesting acquisitions, applications that you can do using interferometric acquisition, and especially having a stack of interferometric acquisition, is the so-called point scatterometer analysis. It means that the system is able, there are algorithms and programs able to calculate the position of single targets, single points which are available on all the images, and by comparing more than 20, 30 acquisitions, you can have the history of the position, of the vertical position of that point. So you can see here is an example over an oil tank area. You can see the mean velocity in terms of millimeters per year. That can be used for several applications. And then you can see on a single point how the point is moving over time. So this kind of application here, it's used for several application domains. So from the stability of buildings, the ground subsidence, so it's not only the ground is moving, we know the ground is moving and has an impact on what's built on top. So we can monitor this very accurately. We have industrial sites, earthquakes and other volcanic phenomena, extraction sites, pipeline dams, viaducts. Here's an example of a stability analysis over a viaduct, which allow us to have a clear overview of a situation. Here it's another example here on the edge of Rome. This is the highway going to the airport. As you can see from the red dots, there are areas where the ground here is sinking. So there is a subsidence problem on the ground, which might not be a problem for the highway, which is monitored, but for the houses which are nearby could be a problem, having the ground that is sinking a few centimeters per year. And so this is something that could be used for applications in urban domain. Of course, you have to take care of other effects which have not related to problems. So here an example on Tower Bridge in London. The red dots is not a problem on the bridge, it's simply a thermal dilation during the summer because it's a metal structure, so it's enlarging during time. Probably you already know that one of the big Copernicus programs is the ground motion service. So this kind of application, the PSP, has been already done over the complete Europe, as you can see from this map, using the Sentinel-1 data. This has been developed, has been produced by a big consortium by several European companies. It's a consortium led by IGEOS. And this kind of mapping has been made already, and it's available online. I put here the link. It's done over complete Europe using a long series of data, and the project is continuing in the future, so we will continue to monitor all of Europe. As you can see here in this example on the left, this is how it looks like. It's resampled, it's a grid, let's say, of stability. Here we are at Castel Sant'Angelo that we saw before, an interesting thermal picture, and the Palazzaccio, the Justice Palace. And you can see here that there is a certain resolution in terms of these dots. So it's about 70, 100 meter spacing between these. This is done with Sentinel-1 data. It's available online for everybody. What is the advantage of using Cosmo? It's to increase the resolution, to have more details. So you see here over the Justice Palace of Rome, there are 4 dots. With Cosmo, you can have much more detailed analysis. You can see all the dots of one of our analyses we made superimposed on an oblique acquisition. And it's possible to monitor the single structure. So here there is a problem on the left side of the basement of the palace, which has been monitored and is being analyzed. And this is a very detailed product and analysis that can be done. The last example is that something that we have made over the Pompeii area, the archaeological site near the Vesuvius. We have done this project together with the Ministry of Culture and together also with Leonardo. And this is an example of the Casa dei Veti. It's one of the major buildings that is in the city, which was subject to a restoration activity. And we monitored, and over some points here, as you can see, there was the roof was a bit going down. So we informed the ISPRA, which is the Italian authority for this for the protection and the working that were done, and they identified that there was a problem and there was an additional support beam in the new roof that had a problem, has to be replaced. So a very precise analysis on a single building during here an archaeological campaign, but of course every building in every situation could be could benefit of this kind of analysis, and especially about the availability of the huge archive that we have of data. As I said, most of the cities, we have more than 10 years of acquisition of interferometric stack, and so we can provide this kind of analysis over most of the urban areas that could be of your interest. Thank you for your time.
Thank you very much, Axel. Are there any questions from the audience? No questions yet? I have one for you. You say that the cities over 200,000 inhabitants are repeatedly monitoring for over a decade. So there's clearly a huge wealth of information and a huge value of this information. I'm wondering, besides some of the very interesting examples you've presented, what are the main applications you derive from this intelligence, and who are your main customers?
We have, there are in Italy, I mean, in Europe in general, in the world, there are some companies which are very keen in doing this kind of application for the PS analysis, and they are having contracts with local authorities generally. They are working on with mining activities, with construction activities, and so there are different applications. There are, so far not many big cities have taken advantage of this analysis, even if many times happened to us that there were some problems in the city, some buildings which were collapsing. Then we did analysis ex after, and we realized, okay, we could have seen this, we could have seen that there was a problem going on. So we are always pushing people and cities to consider this kind of application because of the lot of information they can achieve. And especially if they're doing some activities, just think, for instance, of if you're building a new metro line, of course you're digging a big hole below some buildings, so there might be some adjustments on the buildings on the top, and so knowing how much these buildings are moving vertically could be an interesting information because of the stability of the buildings, especially over urban historical sites, the central part of the old cities.
And just to follow up, now you mentioned this, what would be needed for these large cities to adopt this technology? Do we need better information, more technology push? What's, according to you, a key enabler of the adoption?
I think that in most of the cases, I mean, all this data need to be processed. So they are not processed. We have the stack of acquisitions, so we have to take this acquisition, a certain number of scenes over a period of time, and process the data. The processing, it's kind of time consuming, it's a cost. So I think that in many cases it's simply we need to make a first step into this application, and then the customer will see the benefits, because what they receive, it's a very simple to use the interface. I mean, it's a KML in some cases that you put on Google Earth, and you see all the dots over the cities. You can click on them, have the history, the history of the movements of the points. So it's a really user-friendly application. It's simply that many times there is needs to be done the first step to enter, to see what are the possibilities that you can get from this. Of course, we can provide the samples over some areas, not on every city, because we have not processed all of them, and give examples of how this could be useful.
Thank you very much.
Okay,
thank you.
Thank you.
Next up is representative from Prométhée, Pierre Pommiès, who will talk to us about the Japetus constellation in the making, and how Prométhée Earth Intelligence is offering new decision support capacity to protect cities against natural disasters.
Thank you, Romain. Hi, everyone. I promise I will be sure to be on time for the coffee break. So thanks, Isa, again for the invitation to talk about Prométhée today. So Prométhée, we are a French company. So we are an operator of Earth observation nanosatellite constellation. The company was born in 2020, and we launched our first satellite last year in November. It was a huge milestone for us, a small French company, because we integrate the Copernicus contributing mission in June 2023 with the goal to provide additional data to the Copernicus program. So Prométhée, we are a French company. We want to provide Earth observation solution to address need for sovereignty. In fact, we are more a designer and also an operator. It means that our model, we are fabless. We didn't build our own satellite, but we have designed a whole system from the satellite to the services, because we want to be sure that our data will be used by end users to address the needs of near real-time data today. So we have this holistic end approach, and then of course, so we operate our satellite, but we are able to provide services and also Earth observation programs. A quick look on our business model, but it's not what is interesting today. We have two business models. The first one, Earth Intelligence as a service. It's more focused on sell services and data from our constellation, but using also other data we will come back after later. And we are also another business model, which is to sell end-to-end solution to country, to cities, to, I don't know, industry, who want to have a scalable sovereign on the data acquisition. So our mission is to the iSovereign revisit. So as I told you, our first satellite was launched in November last year. This satellite is more a prototype to prove that our concept works efficiently, but then we plan to launch a full constellation of 20 satellites. This constellation will be, they are satellites of latest generation with a meter resolution, and for that, our first demonstrator we will launch by the end of 2026, and after in 2027 we start to launch the full constellation of 20 nanosatellites. So as you see, 4 satellites will be in synchronous orbit, and the 16 other in inclined orbit. It will allow us to have the more revisit in the European latitude. So we plan to have up to 15 to 17 revisit per day on the same point on the European latitude. And then of course we have the development of our ground segment and our digital platform, because as I told you, we build an entire system and we want to provide this data to the end user community. So the ground segment already works because our satellite was launched and we already provide data. And I will be pleased to show you after the presentation some of our first data. And of course our digital platform that is already used by the French force and in test with other countries. So a quick look on our first satellite, which is already in orbit. His name is Prométhée. It was built by Nano Avionics, and in fact we chose Nano Avionics because we want to be fast in space. It means that the company was launched in 2020, and in 18 months we could launch a satellite. This satellite has a 5-meter resolution and 5 spectral bands. So yeah, it's quite a small satellite for now, but it allows us to prove our ground segment and start providing data and start to calibrate our satellite. But what is interesting, it's our new kind of satellite. So we have been awarded by the CNES, so the French Space Agency, and the French Ministry of Economy to build the new generation of nanosatellites. So we plan to have a 1-meter resolution, also 7 spectral bands, and what is interesting here, it's the choice of our spectral bands. We have decided to have this spectral band to be the same as Sentinel-2 in order to the algorithm we will build already using Copernicus data. We could use the same data the same algorithm for our data. Okay, and we will come back just after, but we also developed connectivity, inter-constellation connectivity. So using our constellation, but other constellation like Kineis, for example, or in Marsat, to have hyper-reactivity. So to sum up our mission for our constellation, so of course it's to have a simultaneous multiple access. It means we can have data everywhere around the world, thanks to the 20 satellites. The intraday revisit, so as I told you, in the European latitude we will have up to 15 pace per day. And also a near real-time tasking and acquisition. Because what we see today, it's when you ask for satellite data, most of the time you have to send an email, but the time between you ask for the data and the time you receive the data is very long. And in order to have this near real-time information, we want to reduce the latency. Thanks to the hyperreactivity, so the interlink constellation, so it means that we will be able to put the tasking inside another constellation, directly linked with our satellite, and give up the information in less than 15 minutes. And of course, we have developed a platform for data valorization and diffusion. So this platform, maybe it's not the most important, of course, because we have the satellite, but we have built it to be the more efficient possible. Today will be the way to directly access to our constellation. And also in this same platform you will be able to have tools, analytics, and also services. Because you will have the 3 different products possible, so the data, the analytics, and the services. And we build it to be the more collaborative platform, because we see that we have a lot of projects in using space data, but most of the time the community don't talk to each other between the prescriptor and the people who made the services. So this platform, we can show you a little demonstration after. We have it in our computer, but show you how it works to share the information between different divisions inside a company, for example, or also between different prescriptors. So maybe now I want to focus on the services we could provide. So what we want is to offer a new capability, and the focus today is on to protect city against natural disaster. So in fact, we used the principle of geointelligence to build our services. It means that we will use our constellation capacity to provide the services. The services is divided in 3 different capacities. And the first one is what we call the situational awareness services, to knowledge and understanding. The second one, early warning system, for the prevention and the planification. And the last one, the rapid response for decision support. We build this unique capacity, it's the base, and then you could address different topics. For example, water resource management, drought flooding plan. You have some of the example here, but we have decided also to be focused on maritime surveillance, for example, and infrastructure surveillance. But now what I'll show you, it's a use case we have for in Porto Alegre in Brazil due to a flooding. So this is the first project I told you, the situational awareness services. So the purpose is to knowledge and understanding for the prescriptor. So in fact, we will use already existing satellite data to provide flood vulnerability maps. Then also we will have different tools like, for example, simulating the rising water levels, and it will provide a map to identify, in this case, the population at risk against a flooding in the area of Porto Alegre. So we don't want to only use the satellite data, because satellite data alone, okay, it provides a lot of information, but what is interesting is to merge all the data we have with already existing data. That's why in our way to work, we work with, in collaboration with our partner, with our end user, because they will provide us their data and merge this data with our data. It's where we're going to have the most information possible. The second product we have, it's the early warning system. So now we're going to use real-time information, such as the meteorological change, and we could provide this kind of map in case of an emergency. Here you have all the sites at risk because we identify that we have a massive flooding, because we have made linked between all the data possible. So we see that, okay, we have a potential risk here. So in red, you will see all the buildings that are vulnerable. So it will provide to the end user the access to how to protect in priority these buildings. And the last product we have, it's the rapid response. And here it's where the capacity of our constellation will be really useful, because we could have access to this information in a very short time. So we could provide information and imagery on operation support for the real-time update. So here you have some example on the identification of affected areas, or also identify areas at population at risk. So this is the product we want to provide. So also data, also services, using this new capacity of high resolution constellation. Because today we see that the number of natural crises increase, and we thought that the satellite constellation are one of the best tools today to respond to have the capacity for the near real-time acquisition. Thank you.
Merci, Pierre. Same as usual. Is there any questions in the audience?
Thank you for this very nice presentation. I just mentioned that you are assigned to build a new generation of satellites, and then you mentioned, So the first question is, what will be the radiometric accuracy of this new generation of satellites? And the second question is that you also mentioned that in that constellation you will consider bringing onboard processing. And then my second question is, which sort of algorithms you are thinking to bring in this onboard processing, level 1 to level 2, or which sort?
So, okay, thank you for the question. Of course, we will. I will answer the second one first. So, we have artificial intelligence on board our satellites. So the algorithms we plan to have for the moment, it's more on the detection. For example, so ship detection, camps detection, for example, but also an algorithm for cloud coverage. It means that if you take the photo and the cloud acceptance, it's good or no, you could directly put another photo. This is the type of algorithm we will put in our satellites, also with the capability to change, because we have a short memory, so to change in the kind of algorithm. For the moment, for the first satellites, they are the algorithms we want to have, but we could also discuss with partners if there are any use for new type of algorithm. For the first question, so I'm just the sales, so the technical question I'm not the best in, but I think it's 30 meters.
Okay, thank you.
Anyone else? No? Maybe I'll ask you one then, because in the presentation there's, you talk about 15 minutes tasking in urgent mode. First, could you maybe describe a bit what it means, urgent modes? Is there a feature of your offering? And second, Could you use any other triggers to be proactive in tasking over disasters and things like this? Do you use any other technology than, any other type of data, for instance?
So yeah, for the first question, how works the hyperreactivity? I will explain to you an operational use. Let's accept that you are a military in the ground, and you have a mountain above you. But you see that above this mountain, you have potentially a risk of enemies. So you are with your space, with your center, with your PC, and you ask, okay, can you please provide me an information about what happened beside the mountain? Okay, so the link is directly, it passes through our ground segments. So our ground segment put the information on the satellite, will pass in the shortest time above a ground segment. So it can be our satellite or satellites from our partners, so as explained you, Kineis, but also we will try to work with Inmarsat, for example. Then the request is directly sent to our satellite, which is in the shortest to the localization. The satellite takes the imagery, analyze thanks to onboard artificial intelligence the imagery taken, and then send back the information to the ground segment. But in 15 minutes, it's just an information. Our operator asks, is there enemy? If yes, how many vehicles? He will only have this information, because we can pass only, it's like short message. And for the second question, yeah, we plan to have artificial intelligence also in our process. In our ground segment roadmap and digital platform roadmap, we want to put artificial intelligence to have labelization between the image, to make link between events. So for example, in the social media, when something happens in social media, you create links, and then you will merge with other source of data. So yes, we try to have not only satellite data, but all the data available thanks to artificial intelligence.
Okay, thank you very much.
Thank you.
Any last questions? If not, thank you very much.
Thank you.
And I leave the floor to Peggy for closing remarks.
Yes, we are wrapping up the session now. First of all, I would like to thank once again our colleagues that have organized the URBIS workshop to give us the occasion to also bring the commercial data into picture. And I think the main conclusion from this session is that there is much to talk about when it comes to the use of commercial data for applications in the urban context. I would like to thank very much to the speakers that have from industry that have come today to present here. So SatView, Constellar, Igeos and Prometi. We have seen very interesting presentations, very interesting use cases, and you got hopefully a nice flavor of what can be done with thermal infrared data, with SAR data, and also with optical data in the urban context. So I hope there will be more occasions for these type of sessions where we can also bring the commercial entities into these workshops. I think that's a very nice combination. I also like to anticipate that ESA is organizing the Living Planet Symposium in Vienna in 2025. There will be more of these type of sessions also in the context of commercial missions. So I hope you will be joining also the Living Planet Symposium and will be able to have more of these type of dialogues. Thank you very much for joining this session.
So coffee break waits for you in the tent, and we reconvene at 12:10. Thank you.
We are going to start in 1 minute. Okay, can I ask everyone to take their seats? And we'll start session 9 of the workshop on innovative downscaling and AI techniques from the new emerging technologies theme. My name is Mikołaj Czerkawski. I'm a research fellow here at ESAFI Lab, and I'm here with...
And I'm from Leiden University and Astral Netherlands Institute for Space Research.
Okay, thank you all for joining us today. This session will have 4 talks, and we'll take questions after each talk. For each presentation we have about 10 minutes, and we ask everyone to try to be under that limit. Depending on how things go, we might give more or less time for questions, but for now, we'll just see where things head. Okay, without further ado, I want to ask the first presenter, Yannis Lantsanakis from Remote Sensing Lab in Iraklio, to present the work on evaluating the performance of the URBIS24 Urban Hyperspectral Library in multi-sensor satellite imagery classification. The floor is yours, Yannis.
And a PhD candidate in University of Freiburg. And today my presentation is about the URBIS24 Urban Hyperspectral Library and the adaptation of the library in different satellite sensors. URBIS24 is a synergy and ARC synergy project that aims to understand the feedback between cities and climate change. A small part of the project is to conduct hyperspectral measurements to get measurements from different materials across Europe. And we have conducted measurements in different cities like Paris, Berlin, and Heraklion. But today the presentation is focused in the city of Heraklion. For the measurements, we mostly use the RS3500 spectrometer. It covers spectral range from 350 nanometers to 2500 nanometer with 1 nanometer spectral resolution. And it has also, together with the measurements, we provide also the respective photo and the GPS location of the measurement. So the spectrometer measures mostly, as you know, radiance, and we are interested for reflectance. So for this reason, we use a diffuse white panel, as you see in the first picture, to estimate the incoming radiation there with the red line. And then we measure the incoming radiation, the outgoing radiation of the material by measuring the material itself, as you see with blue line, and by dividing the 2 lines, we get the reflectance which we are interested for. Additionally, with the spectrometer, we use the high-specs camera, VS620. It has 4 times less spectral resolution, but it can get many measurements with 1 pixel at the spot. And here you can see some of our measurements with this camera from Berlin, Alex Plaza, in 4 different band combinations, where each pixel of the image corresponds to 500 spectral bands. Similar for Notre Dame in Paris, And of course, we have all these measurements, but each pixel is a spectral signature, but we have to select the measurements that we are interested for the different materials, and to label these materials to make them useful. So we organize, after the selecting of the spectra, we organize them using 7 main attributes, which is the material type, the color, the structure of the material, the status, the uses of the material, the city where we get the material, and the sensor where we capture the material. And also we provide a specific ID for each group of this labeling to be easy to find them in the library. Additionally, we force the material to have the same shape, and we force them to have a spectral angle less than 0.11 in each cluster. And we try at the same time to measure the different variation of this material. So for this reason, you see the different heights, let's say, and in different sun angles and orientations, in order to be able to train machine learning and AI models, because we need this variation for accurate classifications. An extra thing we provide is the adjusted spectra for several satellite sensors, for multispectral and hyperspectral sensors. For hyperspectral, for example, for ENMAP and Prisma, and for multispectral, we give for Sentinel-2, for WorldView-3, for Planet, and Landsat. And we do this by using the spectral response function of each sensor. So here you can see for this study, the spectral bands for the sensors we have select, and with dots you see the multispectral, and with lines, with vertical lines, you see the hyperspectral sensor. At the bottom, you see our instrumental, and it's very easy to upscale to the other satellites, because we have at least 2 to 5 times better spectral resolution and at least 10 times better spatial resolution. So we just need to upscale to the other sensors. And of course, some of the bands we have been removed because due to strong atmospheric absorption, that they don't really provide information from the ground. Today, the spectral library only for Heraklion contains more than 5,000 spectra, organized in 260 clusters. And we used a small part of this, we selected a small part of this library to test it in machine learning training. We selected 70 classes from the library for asphalt from 2 different types of aluminium, 2 different types of soils, which is clay and limestone, for cement, for 3 types of vegetation, low vegetation, trees, and dry vegetation, some solar panels, sand, and some artificial materials for sports. And we trained the XSVM algorithm, an algorithm that we have developed with these 70 classes, with 1,127 spectra in total. We used the 70% for training and the 30% for validation. And as you can see, the spectral resolution of Prisma, ENMAP, and WorldView-3 is enough to separate all the spectra completely. And for Sentinel-2, we get some confusion between the soil, the clay soil, and the roofing tiles, which is they have very similar spectrum. And thus, we go to lower spectral resolution like Landsat and Planet. For these classes, the resolution is not enough. So then, after the training, we selected 1 image for each satellite from Heraklion. You see the Landsat, all the images are from the RGB bands. You see the Landsat, the first, second ENMAP, Prisma, Sentinel-2, and Planet, and WorldView-3. All the 5 first are from the same time period, 1 year ago, and WorldView-3 is only for this year. And you see some different colors, mostly because they have different radiometric correction and different atmospheric corrections. For example, Prisma is a little bit darker from the other 2, and Landsat and Planet is a little bit blurred, let's say. And yes. So we adapted the models to this data. And here is the result for a poor radiometric correction. It was darker than the other images. For Prisma, we get a very good pattern, but...
Thank you, Yanis. Any questions from the audience? There's one in front.
Hi, Yanis. Thank you for this comprehensive study. A lot of work involved there. So I was wondering if what would you think about the following? Do you think that you will increase your accuracy if you will also take into account wet surfaces?
Sorry, what?
At the wet surfaces.
Wet surfaces?
Yeah, wet. Wet, I mean, with water.
With water?
So basically, you have some material and then you measure the spectral signature and then you pour some water.
Yeah.
Do you think that taking that measurements could help improve your already good accuracy?
Yeah. We would like to include, for sure, what measurements. There is one difficulty in this, that you need strong sun radiation to conduct the measurements. So if you say that it's a raining day and everything is wet, you cannot measure at a raining day. So it will be challenging to get the measurements for wet materials. Yeah, but let's say if it rains one day and the next day it's clear sky, yeah, something very useful. And probably from Paris we have some of them.
Okay.
But we need to do the labeling, of course. This is the tough part now.
Thank you, Yanis.
One more question.
Thank you for a very interesting presentation and a very novel approach, I think. How did your model perform in shaded areas? In the shade?
Not really well, actually.
That's often a big component in the
there was
urban sphere.
no class about the shades in this classification scheme. Okay. So actually, it selects between asphalt and plastic grass of the football course, let's say. But if we are interested for shaded surfaces, we have to include also training from shaded surfaces to improve the accuracy. Yeah.
All right, thank you.
Any other questions from the audience? This one to the right.
Thank you for your presentation. I have a question. Do you already know, like, what's the variability for, like, let's say, red rooftops between the cities? Is there a huge difference, or?
Yeah. We have measurements from Berlin and Heraklion and Paris from different roofing tiles. But we don't have already analyzed, because you have the measurement, but you have to select the pixels and group them to different clusters and start organize them to the library to be useful. So in roofing tiles, you have huge variation only also for the same material, because it is a very smooth material with a curved shape, and depends when the sun hits direct the material, you have very huge variation from the sun angle. So I think in the sim was from ceramic tiles actually. Yeah. So you see pretty much this is from different angles, these variations from different angles from the sun for the same material. And for Berlin, for example, you have also different colors. You have some black materials, some black ceramic tiles. So yeah, you expect very huge variation. I don't have exact numbers.
Okay.
Any last questions? Okay. With that, I think we can proceed to the next talk. Thank you, Yanis.
Okay, thank you. Then the next presentation will be given by Ricardo from Cutesa, Spain.
So, hi. Well, we are Cutesa, a team working for the project ERIS for Us in support of the European Space Agency. In this project, we are developing a comprehensive change detection of building footprints from super-resolved Sentinel-2 images using advanced AI artificial intelligence models and adapting methodologies to end users. So what are the end users for us? Well, urban planners. So after meetings with them, we identify the requirements and priorities from them, basically are these three. So they are fundamentally detecting buildings footprints accurately, changes from new buildings, and updating their information. Of course, there are some challenges and limiting factors, especially aerial images, commercial, very high-resolution images that have high costs for them. And of course, well, public available data might be coarse resolution. And of course, in the methodological point of view, visual identification and delineation of building footprints is time cost. And of course, if we have to carry out a change detection manually, it can be even worse, because we are comparing sets of time series of images. So then, what we offer to our urban planners, our end users, is a cost-effective solution. And this is mainly summarized in this diagram, where ERIX for us is a full pipeline chaining 3 different artificial intelligence models that use as the main input Sentinel-2 images as native resolution 10 meters, where first we perform a super resolution from 10 to 2.5 meters. This means increasing the spatial resolution up to 4 times. And then the super resolution images are used for a segmentation model and a change detection model to extract the building footprints, which is the result. So then we use as input these images and, well, and a time series for sure for the change detection model. So we're going to see some results first from the super resolution images. So I want you to see this reference image from Google satellite. Yes. So in this Google satellite, we can see an example of dense urban landscape with some patches of green areas, the city center with small buildings, and, well, the newer buildings, group of buildings, right? So then the Sentinel-2 native images at 10 resolution, well, we can see blurry buildings, no identification or distinctions in the city center, well, in the old city center, and, well, the edges are not clearly visible. So once we apply the super resolution, ERIX4, we can see sharp edges, and we can see overall a clear image with individual buildings, especially smaller from the city center. And of course, the green patches are more visible, even we can see water bodies here. But also adding or super resolving the near infrared band, we can distinguish the vegetation from buildings clearer. And of course, the water has a higher contrast because it is absorbing the near infrared spectrum. And another example, again, this is our reference, in a mixed urban landscape where, well, these are chalets, houses, individual with gardens, and we can see also crops, croplands, vegetation, and looks like there's a river there or a stream, and, well, an industrial area. So Sentinel-2, again, at native resolution, we can see, again, we cannot distinguish any building, and these white patches, we don't know what they are exactly, but yeah, we can differentiate the different croplands. Once we apply the ERIX4 super resolution, yeah, we can distinguish clearly the individual buildings, and these white patches are clearly like buildings, industrial buildings. Well, crops, we can differentiate some parts between crops and the texture, or patches, different patches, small parts again, but and of course the highway, which was visible in the previous image, is clear now. And of course, applying the near infrared in this full color image, we can see the string clearly. Then, with the results of applying desegmentation on segmentation on Sentinel-2 native images, we can see that it didn't perform on small buildings, and well, some of the buildings in this part are just joined, so they're not clearly separated. Then, using the segmentation on super resolved images, again, super resolved is applying the ERIX4 algorithm, we can see a clear separation, and of course, due to the limitations of our model, we can see some errors, but overall, the image is enhanced. The segmentation is enhanced. And going to the rural area with individual buildings, very small buildings, we can see like sparse around and in the middle of the croplands. So if we zoom in this area, for instance, yeah, we can see that these buildings have been detected, have been segmented with the algorithm. And of course, now if we compare the identification, the building segmentation with ground truth masks, ground truth polygons of buildings, again with a Google satellite image, we can see first the segmentation from Sentinel-2, native resolution in blue, and then, well, skipping some buildings in the center. And after applying the segmentation on super resolve, we can see these small buildings being, again, segmented. Overall, well, after comparing the segmentation with super resolve and Sentinel-2 native, we can see that there are, 20% in improvement with segmentation of super resolution, and of course the precision and recall the matrices have been improved, so is omitting less and commissioning less. So this helps finally in for the end user, for the urban planner, so they can detect with more confidence buildings. But of course, talking about the change detection, for example, if we take a use case in Madrid, where the Santiago Bernabeu Stadium was with renovations, taking, for example, 2022 and 2023, and using, comparing the results of change detection with the ground truth mask, we can see in black color the agreement of these changes. So black means, yes, I've detected changes here. Well, with a less, or the area of commission and omission are smaller than the agreement. In this change detection algorithm, overall accuracy was 64%, and we see clearly that, under the area of 3,000 square meters, the algorithm is its accuracy, it's detecting 50% of changes over super resolution. We are working with super resolved images from Sentinel-2. So, and of course, higher the size, higher accuracies, in terms of correctness of pixels. So in order to conclude, basically, we can say that, yeah, super resolved images have allowed us to improve the segmentation models and change detection, improving the omission errors, maybe due to smaller sizes of buildings, and commission. Commission is very important for end users, so they don't have false positives. Imagine that, well, I want to see what buildings have changed, and they have a false positive, so they go to evaluate, to assess this building, and actually it wasn't a change. So, and of course, in order to save time, which is a worrying factor for urban planners, we can reduce time for them with an automated workflow. And well, according to their feedback, they can use, but of course it's open to more improvements, this tool. Of course, our next steps overall is to improve the algorithms by adding more bands from super resolved Sentinel-2 images, for instance, red edge or shortwave infrared, refine and improve the training datasets, which are very important for any type of model, deep learning model, and increase the variability of training sets. We've used different topologies of cities. You saw that, well, urban landscapes are like summer houses and dense urban landscapes. And of course, we still have to improve the change detection algorithm. If you have some questions, you can ask me there, and to me, and also my colleague. This has been a work team, and of course, it's from, we are many people involved in this project, so thank you.
Thank you. Do we have any questions from the audience?
I know I skipped some technical parts, but of course, yeah, you can ask me, of course, but...
Do you rely on a custom solution, or did you rely on some benchmark? I'm talking about the super resolution algorithm. I suppose you use a generative algorithm.
Yes, exactly. Okay. Thank you for the question. And of course, we attended some months ago the Suredos conference, and there are like different type of model as benchmarks, sorry. So we use the super resolution, the SRGAN, and super resolving generative adversarial network. It's by the author Ledig in 2017. Okay. So yes.
One more question.
Mm-hmm.
Hi. I'm thinking one of the main problem of super resolution tasks is about artifacts creation. Yeah. How do you know that in that point there is a change, or is indeed an artifact? That's the point.
Yeah, thank you very much for that question. Actually, I'm going to answer it if you want, Samuel, too. It's very interesting topic. The problem with, well, it's not a problem really, but it's about fine-tuning. Super resolution using generative adversarial networks, we know that we're facing the hallucinations. Those artifacts might be hallucinations, so they are giving us commission, false positives. Though, because the algorithm is showing us, okay, here is a building, but well, it's not. Of course, to avoid the hallucinations, first we are taking care of having a good training data set, And of course, the images used are like free of clouds. This is one requirement, of course. Atmospheric correction, bottom of atmosphere, and the training dataset for the GAN itself, the generative adversarial network, is very important for to avoid like unrealistic images. So we are giving very high quality images.
Just to expand a little bit on the answer. Yes, the super resolution will create artifacts. There's no way to avoid it. Not as today, but you have to keep on mind what is the purpose of it. What we are trying to do is identify new buildings, changes, and yes, there are going to be false positives, the commission errors that are shown there. On our numbers, they appear to be quite low. We actually expected more. It's working pretty good. But from the end user point of view, they prefer to have false positives than omissions. Because if I'm trying to monitor the growth of the city, it's easier to go and check if a building is really being built in a specific place than omitting one. And if you are having, let's say, 60–70% of success on identifying the new buildings that are appearing in the imagery, you are cutting a lot of work from the people that works in the GIS department of the municipality, and you are just giving them a smaller task, which is making that validation of the data. And it's easier to validate 3.54% of commission errors than having to identify 100% of the changes. So it's a little bit, again, you are going to have hallucinations, let's call it that way. But on a business side, as a tool to improve your performance, it works.
Yeah, exactly. If you offer the end user, the urban planner, a solution to decrease the time to do a task, it will be very welcome, of course, with a high confidence level.
Any other questions? There's one in the back.
Yeah, for me, thank you. We talked already previously 2 days ago, but I'm more interested in the change detection because you didn't describe it super in detail.
Yeah, no,
I'm curious if you are using just 2 images or a larger time series. And second question, if you have, for example, especially for the change, a filter of area, because normally, since you are doing super resolution, like maybe, I don't know, you decided to quit a certain change that is under a certain area, or yeah, maybe you can be more detailed in that. Thank you.
Yeah, of course, thank you. So if I understood correctly, well, first question related to change detection, we use a UNet++ model, and we take into account the changes by comparing, well, the training, of course, has been done with a time series of several images, and then for inference, we are using like 2 different years, as you've seen in the example. So, and the masks, the true masks, are pointing to changes occurred in the urban areas and buildings. If that answers the second question. And 2?
I don't know, I mean, for example, you detect that it's just a random case, 1 pixel of change. Are you keeping it or you are filtering it? You just post-process your outputs? Yeah, maybe this is clear.
Yeah, the post-processing requires still a post-processing, filtering.
Okay.
And of course, this is also part of our next steps, just to fine-tune the change algorithm to avoid this
clear.
Yeah.
Thank you.
False results.
Any other questions? If not, I think we are ready to move on to the next talk.
Thank you.
And the third talk from the session is on the topic of super resolution of Sentinel-2 and PlanetScope EO images, comparative study presented by Roberto Cili from University of Bari.
Can you hear me? Yes.
Yeah.
This works. Okay. Thanks for inviting me. As you may guess, I will show you. Yes. First of all, I'm Roberto Cili. Sorry, I didn't present myself. I'm a research fellow at the physics department of the University of Bari, and as you may guess, we'll talk about image restoration technique for some medium resolution products like the Sentinel-2 and Planet-2 scope products. Okay, let's start with the outline. Yes, of course. As you may guess from this picture, our goal is to develop an image restoration model capable of producing, hopefully, area-like imagery when fed with medium resolution products like the 10-meter resolution Sentinel-2 or 3-meter resolution PlanetScope SuperDAV. And here we can see a close detail about how the image look like. In particular, from bottom right to top on left, we have very high resolution image acquired from a drone, from a Magellan sensor, having a resolution of dot 375 meter and dot 75 meter resolution. And then we have an actual PlanetScope SuperDAV product and a 3-meter super resolution product. This is a synthetic image downscaled from the actual MicaSense image. And our research project, our research question is whether we can find in the literature or develop by our tools a method for coming from images looking like the one of the top to images looking like the one of the bottom. So this is the outline. I will define better our problem. I will describe the data set used in this study. Then I will move to method and evaluation metrics adopted for this study. I will describe the experiment, then I will conclude this talk. So we use as a case study very high resolution images acquired nearby the urban and peri-urban areas of Andria, which is located in southern Italy. We have collected in particular images from the PlanetScope SuperDAV and MicaSense, but since acquiring image from drones and PlanetScope is costly, it has a cost, we couldn't cover a large area, so we had to rely only on slightly less of 1 square kilometers of area. And then we have for year 2019 a wide area covered by aerial imagery, but unfortunately only on 3-channel RGB. And on the left you can see how the image look like. On the top left you can see an actual Sentinel-2 image, so how it looked like, and on the right you can see an actual PlanetScope, and on the bottom we can see our target, or our desired target actually. And here we have the experiment. In this talk I will talk only about single image super resolution. We use the super resolution GAN algorithm from Ledig et al. 2017. And we'll just describe the result of 3 experiments while I prefer to keep in backup some failed experiment when I try to use other layer information with higher resolution to improve the result. But of course, they are in backup, so I failed. So here it is the method I used. It is a super resolution GAN. We can describe 2 main units: a generator network that learns to synthesize a fake image or super resolution image, and a discriminator network that learns to not be fooled by the generator. When everything goes well, we will end up with a generator that learns to actually synthesize a good image, and a discriminator network that does not have any clue about which image is fake and which image is actual. So our target function will saturate and will not neither decrease or increase. And in this target function, we have two contributions, actually. One is the contact loss that measures how the fake image looks like the target one, and the discriminator loss that actually measures the capability of the discriminator module to discriminate fake images. So let's move on, and these are our evaluation metrics. I just decided to focus on, let's say, a quantification of overall quality of the restoration algorithm I trained, and I use only one metric, which is the peak signal to noise ratio, which is it is proportional to the logarithm of the ratio between the maximum intensity on an image. Here it is 255 because I used 8-bit images, and the square mean error. Sorry for the mistake there. And these metrics range actually usually value between 20 to 30. It can be even greater sometimes. But here I define a rule of thumb just to be clear about the overall quality of the restoration process. All the pair of image that has a PSNR less than 26 decibel, they are poor image. From 26 decibel to 28 decibel, we will say that image quality is not perfect, but I mean, still lacking, but still maybe useful for some task. And above 28 decibel, we have good but not perfect quality image. And here we have a first result. Here we train a resolution gain of 8 times. And maybe it was too challenging, this task. Consider that we just use a single image super resolution. And here we have a close-up look of all the images. We have an high resolution image where we can see some trees, a paved road, and some vine rows. We have a synthetic Sentinel-2 image where we can barely see the road, and we have a super resolution image where we can actually see only the roads and maybe some artificial land cover, like building, not too small building, and other artificial landscape, but we miss all the information about trees. As you may guess, here we have very low restoration, a very low quality of restoration. In fact, we have a PSNR which is below 22 decibel, which is no use. No, we have no practical use. We have images that are too blurred, not radiometrically accurate, and maybe even too few examples to train a model. We believe that probably Planescope images do not offer, let's say, a product which is radiometrically calibrated. So we think that despite having this high resolution, we couldn't achieve great result. And here we have some result that we achieved with the synthetic image having a 3 meter resolution, just to prove that maybe there could be some room for reaching area like imaging from medium to high resolution products. And yes, these are other examples. This is in this case, we have just a less challenging task, which is 4 times resolution gain. And we have quality index, which is enough good, pretty good probably. And here we have our conclusion. So we believe that it's unlikely to reach sub-meter spatial resolution using Sentinel-2 or SuperDAV product so far. While Planescope offer a higher image resolution, this image appears blurry, not radiometrically accurate, so there is no room for improvement of this image using generative algorithms. And there is another conclusion. This is a good news. We believe that using a 4 times super resolution model trained on synthetic pairs and not on actual synthetic Sentinel, not on actual synthetic actual Sentinel-2, sorry, Sentinel-2 products may lead to some model that could be transferable, and so we can use this. We probably can use this model to actual Sentinel-2 images. Our future perspective is to design or search for a super resolution algorithm that may use multi-sensor aggregation to just to increase the resolution gain, and or increasing the PNSR. That's everything. Okay, thank you for your attention.
We can now take questions. There's one in the front, there's 2 in the front, okay.
Thank you. Yeah, so impressive work, and it's I guess it's very difficult to super resolve to spatial resolution of unmanned aerial vehicle. Well, make a sense. But
yes.
Yeah, in this case, how many images, training images did you use? Or
6,000 training images, and I tested on 6,000 training and 700 tests. I didn't perform any cross-validation due to computational cost.
Yeah.
So of course all the metrics are without any error, because computing error would be costly.
Mm-hmm. Were all the images taken from drones? I mean,
aerial. This one. I used the drones are
exactly.
Drones images were acquired only for a small area, less than 1 square kilometer, not enough to train a robust classifier. So I instead relied on synthetic pairs. So I just downsampled aerial images, and I rely only on 3 channels.
And is it apply only to one specific, vineyards or? Well, your study area,
most of the images cover agricultural fields, but we have also some pictures of the city center of Andria and other small fractions. So,
wonderful, great, thank you.
So, but mostly, yes, it's agricultural.
Yeah, well. I hope you can get better results afterwards and apply at least for coastal wetlands. It's also challenging.
Yes, because it's I'm, as you may guess, I relatively new to the field. So this was just an exploratory analysis, just to have some metrics or some indicator that could give me some insight about what actually we can do and we cannot do about. When we talk about super resolution. Yeah. It's a nice topic. I really like this topic. It's challenging. I want to know more and even testing more architecture for sure.
Well, thank you very much.
Yes, thank you very much. That was quite impressive work. I was wondering, I actually have 2 questions which are related. One of them is about the spectral differences that may be between the MicaSense and the other sensors. If you can comment anything on that. And the second one is about the accuracy problem that you see in SuperDAVs. Is there an accuracy problem? If that is the case, would extra calibration help? or if it's a precision problem and then you cannot do anything about it.
Okay, regarding the first question, I can give an answer. About the second, I don't know enough to give an answer, so I will not answer, because I'm not an expert about calibration, validation of products. So I don't know enough about Planet DAV products. But about the first answer, if I understood well, the question is about the channels of the drone sensor. So actually we have 10 channels, 10 channels in the optical spectrum, plus a brightness temperature channel. But in order to have a matching between planet scope channels and channels from the Mica sense, I just selected 3 bands, which were actually the green, the red, and the near infrared, which were matched actually. So I work on a false image, on false color images. About the second, I can't give you an answer, but nice question though, because I need to understand whether maybe other acquisition, because I work only on acquisition, on a single acquisition, maybe there are other acquisitions that maybe they may give some clue, give more clues about the image content. Yeah, of course, and the first image, we do not have any idea, especially in this one, we have any idea about what there is behind. We have only some different shade of red, sorry. So yes, maybe it could be a problem of calibration, I don't know.
In that case, I think it's more, in the 3-meter resolution, I think it's more about what you mean by resolution. What do you mean by resolution, right? There is a huge difference.
The one declared by the product.
Yeah, no, of course, but like resolution is not a very strict or very informative word. Like sometimes you mean ground sampling distance, sometimes it's ground result distance.
Yes, that's the ground sampling distance according to the data sheet of PlanetScope.
Yeah. No, but maybe it's their optics is a little bit worse and you have more spread out.
I don't know.
Yeah, I know. Well, thank you so much for the.
Thank you.
One last question.
Yes.
Just to add a little bit more, the first image is
which one?
The 3-meter resolution is native or not? Yes, the first one from
first
the left.
one left.
Yes.
No, it's a downsample image from the Mica sense. The actual resolution of the Mica sense is 10 centimeter.
Okay.
So I actually downsample all the images you see in the slide.
Maybe one of the problem could be also the type of resampling strategy. I suppose that here you used like nearest resampling strategy that is not useful or feasible like directly to 3-meter resolution to actually
mimic
the 3-meter resolution of a PlanetScope. I had used something like an average here. Maybe.
So instead
but
of a bicubic interpolation, something linear.
Yeah.
Ah. Okay. Nice to know. Okay.
There's quite a lot of work in the computer vision field about estimating the downsampling kernel from real images, and that's a whole field that you could potentially look into, because sometimes you can estimate this from the data itself as well, which could be quite useful, because like bicubic or linear or nearest neighbor, I mean that's something you will not see in physical instruments, but you can often estimate from the data itself the way the spatial relationship between different sensors. And with that, if you incorporate that into your super resolution model, you should potentially be able to produce better downscaling results.
Thank you for the advice.
Yeah, and it's the same thing for And it's the same thing for synthetic versus real data sets. There's also some interesting studies on that, and that actually what you're doing with the real...
Which study?
So maybe I can send you a link later.
Thank you.
I think there was like an interesting paper called Kernel GAN. If you look into kernel GAN, they basically try to estimate, not for satellite images, but for general images, for super resolution of natural images. There's quite a lot of work looking into that.
We need to talk.
Yeah.
We need to talk more and better. I mean,
Absolutely. Okay, thank you. And we're now ready for the last talk of the session.
Yes, so we invite Niklas Simonsen, who will speak about human in the loop, empowering urban environmental monitoring with flexible cloud-based satellite mapping workflows.
Thank you for the introduction. I'm going to introduce myself again. My name is Niklas Simonsen. I work at DHI in Denmark. I'll be presenting Human in the Loop, which is we try to empower urban environmental monitoring with flexible cloud-based satellite mapping workflows. So currently we have a myriad of global and regional products available, and you guys are all familiar with this. This is what powers what we do and allows us to do a bunch of global analyses and regional analyses and countrywide analyses. We have from commercial vendors like Google and ESRIN. We have non-governmental organizations like ESA and Copernicus and the World Bank, of course. Sorry. Some of the advantages this provides is that it has a really broad coverage. We can cover the entire globe, and it's so easily available, right? You just click an area, you download it, and you can compare it across different regions. It's a one-to-one. A building somewhere in the US means a building somewhere in Europe as well. And we can compare across time as well because it is standardized. You know, we have products going 16, 18, 2020, and we can use these to account for land cover changes on a broader scale. But some of the issues with these data sets is that they often lack this fine spatial resolution that's required for precision urban planning or looking into where we need to put more trees, for example, like we've heard again and again over the last few days here. They may not also generalize very well, depending on where they're trained. If it's a global data set, it usually hits a good benchmark across the board, but that may not be applicable if you're living in a city that's not representative. If you live in the very north or the very south, we see that these cities are not well represented by these global data sets. And additionally, there's an issue of latency. Some of these products are updated infrequently. It's not weekly, it's not monthly, it's sometimes yearly, or it's every other year, and sometimes it's even like a rolling update. So you'll have one place updated and the rest is sort of waiting until it's their turn again, and then they redo the whole globe. So we think that a new agile framework is needed to address some of these issues. So classically, we have manual digitization, which a lot of us has been through. We know it's highly accurate, it's very flexible, but it is incredibly time-consuming, which is why no one does it anymore. Not really, at least. And then machine learning, which has gained so much notoriety lately in the last 10, 20 years, as this groundbreaking thing, right, that can save so much manual work. And this is typically trained using either some data collected in field or by manual annotations from remote sensing data. And the methods in machine learning have differed over time and still do differ quite a bit. We have classic methods, that's just simple thresholding. And we have random forest, which is an incredibly clever algorithm that looks on single pixels. And then we have, more recently, the deep learning algorithms that look at the context as well. So they're becoming smarter as well. Our workflow is sort of taking, I wouldn't say a medium approach, but it's a rather novel approach. So what we do is we train these models for different resolutions. We have Sentinel, we have VHR data, we have orthophoto. We train different models as well for different issues. What the user can then do is they can provide either their own input data, VHR imagery or orthophotos, or they can pick Sentinel-2 imagery from the whole archive. They can choose whatever model they want, whatever problem they're looking at, and they can generate an output. If they're not satisfied with the output, they can go back, they can redo some of the annotations, like some buildings are not captured correctly, you know, tile buildings, whatever, or the beach is not captured, right? let me make a little bit more annotation data. I rerun the model, takes some minutes, and you get a new output. If you're satisfied, you're good to go. Otherwise, it's an iterative process. It's an incredibly versatile platform, as I mentioned. It's trained across a bunch of different resolutions, and as I also mentioned, you can choose between different pre-trained models for the urban sphere, like land cover classification, roof segmentation, roof type classification, and tree inventory, which is some that we've heard again and again here. And we're adding more models to this as we see fit, or as the user sees fit. One example here on the very right is a tree inventory for the city of Copenhagen that is just plug and play it basically with some high resolution imagery, either orthophoto or neo. Of course, you can do this in Sentinel as well, but you'll miss the fine scale. I'm going to go through a few examples from the products that we've developed. This is for the city of Gothenburg, where the user had some neo imagery. The plate is neo at 0.2 or 0.3 meter resolution. So they can go in and they can find all the individual trees down to about, I think it's 3 or 4 pixels. So you're talking something with a crown canopy cover of 1.2 meters, which is most trees in the city. So what the advantage of this is that the municipality often has some data available. They have mapped, let's say, 30 or 50,000 trees, but this, of course, does not cover it. And this is only publicly available trees. So they can go in, they can upload their data to fine-tune the model to create a really good result for their individual situation and their individual cities. Secondly is a classic land classification. You've all seen this. This is nothing novel, but our solution allows the user to adapt it to their needs, to focus on specific classes or specific resolutions available, so they're not stuck with a 10-meter resolution. If they have orthophoto available, which a lot of European countries do at least, they can use that one for classification instead. And thirdly, it's roof types. We've seen that this has become increasingly popular to map roof types, both because of the heat signatures that's required or from the different material types, but also because when you're doing, let's say, hydrological modeling, you need to know what roof type you're actually looking at because of the different runoffs from the different roof materials. Something like metals will often leak certain what's called pollutants into the ground, which you need to keep track of as a city. So some of the key benefits of this approach is that you have an increased data accuracy over generic models that are plug and play, because you can go in and you can tailor this to your specific area, and additionally you have an extra set of eyes on it that you don't have with global models, because you have a user going in, checking, does this actually look representative of my area, and if not, you can go in and you can tweak it. And again, this is a tailored solution to the specific city that needs it, because we work with a lot of smaller cities that are less than 50,000 people, and a lot of these big data sets, they don't quite capture the variation they need for their city. Additionally, there's also a continuous learning aspect, both from the model, but also from the user, as they get more used to sort of the training data and working with this sort of data. It's a two-way street, but also they have the ability to upload their data to our models and keep improving them with a little bit of quality control, of course. And we also see that this has increased stakeholder engagement from the users. They get to upload their own data, and they get to use the data, and they get to refine the data. It fosters a data ownership, so they feel like this is their product. They've helped build this, instead of cutting out a global model and saying this is what everyone uses. They can go in and they can make their own products here. And perhaps lastly, I want to stress that this is a very scalable and flexible solution. It can be deployed across a lot of different cities at various scales. So you can accommodate data availability. If you have nothing, you can run with a 10-meter model. If you have orthophotos, you can use that. And if you want to buy VHI imagery with additional bands and get additional detail, you can also do that. I just want to touch upon briefly some other solutions that we did to inform the urban decision-making for cities. We've looked at mapping the 3-30-300 rule. I've not seen it mentioned yet, but it's quite popular in the US. So basically, it states that 3 trees should be visible from every single house. And for your neighborhood, 30% of the area should be canopy cover. And within 300 meters of your building should be a green space that you can access. So we take our tree inventory, we take our building footprints that we can either find or we can generate. We do some geospatial operations, a little bit of machine learning, and you generate an output that sort of shows where the focus is maybe needed. These people don't have access to green spaces, these people don't have access to trees, etc., etc. You can combine these scores for a sort of a metric to say that this is like the most critical area that we need to focus on because these people have access to nothing. It's a scale of scores as well, so you can score very high, you can score very low, and that helps the municipalities and the stakeholders to sort of harness or focus their efforts where it's most needed. And secondly, it's the tree equity score, which again has been seen quite a lot of notoriety in the US, but has not been mapped so thoroughly in the EU yet. So again, it focuses on tree canopy cover. It focuses on a bunch of demographic factors, and it focuses on the environmental benefits of the individual trees. And again, this is mostly just to kind of guide stakeholders as to where you should plant the trees. It incorporates a lot of socioeconomic factors as well, like income, age, and that, just to sort of, again, focus the efforts of where it's needed the most. For example, older people and younger people are often more exposed to heat stress, so this is an area that should be focused on. And yeah. So just to summarize as to why we should use Earth observation and AI for urban decision making. For the human-in-the-loop approach, we offer a contextual accuracy. By incorporating this human expertise, we ensure that the AI-generated insights and machine learning insights, they're relevant and they're tailored to your solution. As either a medium or a large or a small city, it doesn't matter. And again, the stakeholder engagement is super important to get people involved, the people that need the data and the people that use the data. Because without them, you're often talking, in parallel. You're not talking to each other. What do you actually need? What problems are we trying to solve here? And how do you want the data to be? And thirdly, it has the continuous improvement aspect that users can keep sort of working on this by improving the accuracy over time, and also they can rerun it at different times. You can get a classification now, you can get one in 6 months, etc. And for AI-driven insights, it offers effective or efficient data analysis. We can process large volumes of data quickly, we can provide actionable insight, identifying trends that might not be visible through manual input. Because all this is cloud-based, so it runs in real time. You press the button, you generate an output, and a couple minutes later you have a map. And then predictive capabilities, the machine learning models, they can forecast future urban challenges as well, such as traffic congestion, environmental impacts, such as which can help with proactive decision making. And then finally, the data integration. The machine learning can synthesize data from multiple different sources, and it can offer an extensive and comprehensive view of the urban dynamics by facilitating or help facilitate a holistic policy development. Some material afterwards if you want to get in contact. Otherwise, thank you very much. The slides will be available, I think, at the end.
Thank you, Niklas. Okay, before we head to lunch, I think we have time for a few questions. There's one in the back.
Thank you for the wonderful presentation. I think it's a really nice idea to engage the users to be part of the model training process. And I have two questions. One is about what if the user introduce outliers or errors when they uploading their data sets? Would that mess up with the model you have? And then probably the errors would propagate. Second question is about the, would it require any technique capabilities for the users from different cities? Then that probably means that the city needs to build up their capability for, engage in this process using your platform.
Yeah, so I guess the two are sort of connected. If you have technical users, they're less likely to make outliers, right? Because they know what they're doing. But to your first question, yes, people do introduce outliers, and yes, we do screen for them. We have automatic tools, and we also go through it sort of to assess like how does the accuracy actually perform in other places that the model is not being implemented at. Are you actually sort of making it worse? Because then you're probably introducing outliers. But let that work in isolation and then not introduce it to sort of the main model that's working behind it, because people have reason to introduce these in the first place, and we don't want to say this is wrong, but maybe just give a little guidance sometimes. For the second question, no, there's no technical expertise needed. We have people with no JS background, you know, from social backgrounds who just, because it's a web platform, you just go in, you just click on a few places, you draw a polygon, like you would do in Earth Engine, or not Earth Engine, in Google Maps, for example, or Google Earth. So it's very simple, and then you can upload it and you can check the results immediately.
Is it that for the user to decide it's enough, or the model give a satisfying performance, or it's actually your organization like co-deciding with them together?
Yeah, I guess so. There's two ways you can do it, because you have the training data. So you can either check how the model is doing against your training data, or you can use the training data or parts of it to improve the model, and then test against the rest of your training data. But you'll get a metric out scoring against sort of a regional data set at least. So you'll get an accuracy score for other places that you did not draw in, and also for the rest of the city that you have drawn in, not incorporating the new data as well.
Thank you.
Sure.
Any more questions? If not, I have a question. So you've shown quite a few interesting use cases for your platform, and unless I missed something, most of them were based on very high resolution data, and that's something you can usually do in places like Copenhagen, where you have access to really high quality data. But have you experienced anything where you use this platform with low resolution or medium resolution sources like Landsat or Sentinel?
Yes, so we have not used Landsat for this, but we have used Sentinel because it has such good coverage in Europe. We're not working with land surface temperatures for now at least, so there's not so much need to incorporate Landsat. But I mean, again, as mentioned, there's a lot of really good data sets for Sentinel out there already, but you can improve on them. Again, our model is trained on a lot of the same data that these models are trained on with Sentinel. So if you want to go in, you can improve let's say, your forest classification or whatever, but you won't get that really fine detail, of course, from individual trees. But yes, it absolutely works with Sentinel.
Okay.
I just figured that you've all seen a Sentinel-2 land cover classification. So
we've seen plenty, yeah.
Yeah.
Any other questions? If not, I think we can head for lunch and consider this session complete. Thank you everyone for attending, and thank you for all the speakers for presenting their work. It's been a pleasure to host the session, and I hope you enjoy lunch. And one notification is that I think the other session is running a bit late, so we might have more time for lunch than according to the schedule. So no rush. Take your time.
Somebody wants it.
Where's the timer? Timer. Okay, no problem. I have also my phone to sign up. Where's the presentation? Why? Why the first one? Well, the good point is that it's just after lunchtime. Most of the people are sleeping. Yeah, it's good. It's good. Okay, so we have 12 minutes. I have to go just downstairs to see the shop. Buy anything.
videos too. I was trying because I didn't. I know. But see, I went all the way to the big hall. And he was on the chair. He wasn't. Yeah. So I got a shit attack because he wasn't with all the other nameplates. No? I said, oh gosh, I can't believe it. And somebody else said, no, but it's there. I saw it this morning. It exists. No, we put it together with the calculator. Ah, okay. So anyway, we did it.
Yes.
Phone
somewhere. Check it. For example, here. Yes, so we put the timer.
It's 2:30. I suggest that we wait for a few minutes. I guess there might be some people a bit at the canteen yet still, so let's wait for a couple of minutes and then we start. Okay, I suggest that we start. We are 5 minutes late, but I think that's fine. So this session is about advancements in 3D urban modeling, new emerging technologies, part 2. I will be one of the co-chair. I'm Nicolas Mjepe, and I share this session with Alessandro Sebastiani. We are both at the PhiLab, which is kind of disruptive lab in ESRIN. Yeah, we'll have 5 talks. I propose that we have all the Q&A just after the talk, so 10 minutes talk, 5 minutes question, and so on and so forth. Okay, I invite the first speaker, Babak Mema from University of Sapienza in Rome, and he will talk about deep learning architecture for 2D, 3D joint change detection in new areas. Floor is yours. Go ahead.
Okay, thank you so much. Hello, everyone. Good afternoon, and I hope you have had a beautiful day today. So let's start. So by the year of 2050, it is predicted that 70% of the Earth population will move and live in the cities. So it is essential to make the cities safe and sustainable, and that is why the UN makes one of its goals in this direction to make the cities safe. So it is essential to work on urban areas and try to work on different properties of this area. So we work on the change detection in urban area, and then we ask, okay, can we use the high-resolution SAR images to detect 2D and 3D changes together at the same time with less cost? And then we say, okay, let's try. We have, at the first point, we want to work on the change detection to find the areas in this urban that's the change happened, and then try to see, okay, if these changes belongs to the 2D changes, and at the end try to see to calculate the height of the buildings to see the 3D changes in urban areas. So we are here. We want to focus on all these 3 works together. Our study area is Milan in Italy and also Berlin in Germany, and we use very high resolution Cosmos Sky Met images, 2.5 meter. And also Trusar X images from 2019 to 2021, and the data sets as a ground truth for containing the building information, height information. We use these data set provided by municipalities of Berlin and Milan. So we divide our work in 3 different steps. In the first step, we focus on change detection. So for that, we try to use a time series of very high resolution images, and then calculate the coherence of every 2 adjacent images in our time series. And because we just want to focus on the urban area, so we try to extract the urban extents using, again, the time series of very high resolution images. And then calculate the urban core and mask all the coherence images by this urban core. After that, try to calculate the sigma over mu, and following by auto-thresholding, we calculate the inner change map. And at the end, using an unsupervised k-means, to classify the area to 3 different clusters: the unchanged area, the area without any change, the area that there is a construction, and the area that there is a deconstruction. You can see on the right top that's okay. You can see that this is the first image in our time series, belongs to 2019 January, and this one is 2021 December, and we use corresponding RGB image to just show that, okay, in 2019 there is a flat area here, and in 2021 there are 2 buildings here, and our algorithm can perfectly detect these changes over time. In the next step, to find out the 2D changes, we try to use a units algorithm to do the footprint segmentation in our region of interest. So we trained this model with the first image in our time series, January 2019, and then try to use the unit model, as you can see, that contains the encoder and decoder part, and at the end we have as an output the footprint of that area. Here there is an example of our testing data set that you can see on the left. We have the testing labels, and on the right it is the one that our algorithm predicted, the footprint of this area. And we published this work on the IGARS 2024 that is accessible from this URL here. And in the last part, for the phase 3, we use the idea that is published in this work, that they try to use the relationship between the SAR image coordinate system and the actual buildings, in fact the UTM coordinate system in the SAR images, that there is a relationship between the length of footprint and the height of the building. So they try just to calculate the footprint bounding box, and based on that, with calculating the building bounding box, they can use this equation, H equal to L divided by cosine of theta, where theta is the incidence angle of the images of the satellite, and then they can see the height of the building. So we get this idea and try to define our network, our model using a ResNet 101 with 3 different inputs: the SAR images, the footprint mask, and also the footprint bounding box, to calculate the building bounding box at the end. And we also consider the orbital path of the satellites because as you know, the satellites look at the buildings with a certain inclination angle, and we consider this in our work to get the better result. So here you can see one of our results in the city of Milan. In the left there is the ground truth height map, and the one that predicted, the height map that predicted with our work. And in this test area we can achieve the mean absolute error by 1.5 meter. Okay, so at the end we have 3 different steps. First, try to to detect the changes in the city. Then try to see if there is a change in the 2D, in the footprint of the buildings, and at the end try to calculate the height of the building to see if there is a change in the height of the buildings, in the 3D changes in fact. So this one is a very good example of an area in Berlin city that you can see. This one belongs to, this image belongs to 2019. In this area we have 2 small buildings. And in 2021, this one is the same area that these 2 buildings are deconstructed, and another building is constructed here. So you can see in the first step, we can change the detection, we can detect the changes in this area very well, and then focus on this area using the first image in our time series that belongs to February 2019. And also the last one belongs to December 2021. And then calculate the footprint in this area using the units to predict the footprint. And you can see that, okay, we have changes in the footprint of the buildings that shows, okay, there is a change in 2D. And then try to calculate the building bounding box based on our algorithm that we use, the ResNet 101. And here you can see that the red area is the building bounding box, the green area is the red area is the footprint bounding box, the green area is the building bounding box, and based on the difference between these two, we can calculate the height of the building in 2019, and here in 2021, and here is the result. In 2019, there was a building with 3.55 meter, and in 2021, it is 17.5 meter. And our algorithm predicts the height with a very acceptable difference. As you can see, the absolute error here is just 82 centimeters for 2019 and 1.7 meter in 2021. Okay, so our innovation in our work, just to conclude, is to try to focus on both 2D and 3D changes in urban area at the same time. And as we can see, we can detect the areas that have some changes during the time, then predict the footprint, calculate the footprint, and at the end predict the height of the buildings with, for example, one of our region of interest with 1.7 meter, the mean absolute error. And for our future work, we will try to make it more scalable, work with different data sets on different cities, and also try to add some new methods to deal with the shadow of the buildings. And at the end, further, we will try to see if the use case of the buildings is changed over time or not. And if you want, we will be so glad to have a connection with you. I hope we are trying to work together in the future. Thank you so much for your attention and also your time, which is your most valuable asset. Thanks.
Any question for Babak? No, if not, I can start. I'd like to know more about the ground truth that you use. What are for you the way to check the quality of your algorithm for change detection, for 3D change? I mean, how did you validate that?
We use the data sets that provided with municipalities, so we just focus on their data and then try to use the height that they provide us for each building, and then we focus on each building separately, calculate our prediction and also the actual height, and then try to evaluate our work.
Okay. Second question I have is that, okay, as a perspective, you mentioned that you want to scale up to different regions, cities, and so on. I see that here you are using 28 Cosmos KMed and 35 TLSX, which is quite expensive at the end. So if you want to multiply to different cities, I mean, what would be the cost for that? Is that really scalable? I mean, this technology on high resolution but very costly images, I mean, do you have a feeling on that?
Based on our contract, we have access to these two data, fortunately. But to be honest, we most focus on the second and the third step, which can provide information about the footprint of the buildings and also the prediction of the height of the buildings, just with only one high-resolution image. So ignore that. If you see the most important, your question related to the first part, in fact, the change detection area. So we will try to see if there is another way to calculate with fewer images the change in that area or not. And we are focused on that in the future, and we will try to make it less cost.
Any question from the audience? No? So let's move to the next speaker. Thanks.
Thank you so much.
Okay, our next speaker is Thomas Esch from DLR, and we'll talk about the global analysis of 3D settlement morphology and its relationship to economic and planning condition. The floor is yours.
Thank you very much for the introduction, and it's my great pleasure now to present you some joint work of DLR and colleagues from the World Bank and from the George Washington University, where we try to, let's say, go for global analysis of the 3D settlement morphology and took a look at the relationships to economic variables, but also to planning conditions. So it's still ongoing work, but this is, or what I will present now is some first results. So regarding the motivation, the basic driver behind that was to support the SDG 11 goal of the United Nations, so make cities and human settlements inclusive, safe, resilient, and sustainable. Of course, if the planners and decision makers want to do so, they have to develop a sound understanding about where and how, under which conditions the people live. And we all know, and we've heard that already in the last 2 days, that especially in the global south, this is still a big challenge. So to get up-to-date and information and data, and also get a frequent update, let's say, of the situation, how it develops. And that's why we focused on coming up with consistent, up-to-date and accessible data and information for these purposes, especially on the built environment. And our, let's say, instrument and tool to do so is the World Settlement Footprint, WSF. And we had even a predecessor, which was the Global Urban Footprint, where we started in 2011 with the first global map. And now, as we have seen, maybe with a talk from my colleague Mattia Marconcini, it's an entire suite. And what I will now introduce to you and show you is the WSF 3D. So it's a global 3D estimation of the building height, building volume, etc., that we then combine with other economic data sets. So basically, the World Settlement Footprint 3D was released a few years ago. I think at that time it was the first worldwide 3D mapping of the entire built environment at 90-meter resolution at that time. It's also published here, the methodology. Just going quickly through it, basically what we do, we make use of the 12-meter digital elevation model collected in the Tandem X mission, where DLR is also running part of the processes and the production. And then in simple words, we looked at the EM within the build-up areas masked by our World Settlement Footprint binary masks, and then looked at the height jumps, let's say the height edges that we discovered, and thought that usually abrupt height jumps in the height model should be allocated or be in line with building outlines, or height differences at building outlines. It's this data set here. And then we also used Sentinel-1, Sentinel-2 collections, multi-temporal, to estimate also the building coverage. So per 10 by 10 meter cell of Sentinel, we estimated what the building footprint is. And finally, we could combine this information to bring out our 90-meter Tandem X data, World Settlement Footprint data sets. You might wonder why we analyzed 12-meter data, but at the end come up with 90-meter resolution. That was simply a condition, since the Tandem X height data is due to a German data security law, and the Ministry of Defense didn't allow us to come up with the full resolution, so we had to degrade, actually summarize the statistics at 12-meter to 90-meter cells. And the products that we have are the per 90 meter cell, the build-up area, so build-up footprint, the average. We have the height, so the mean height of the buildings within that, and of course we have the kind of average height if you even consider non-build-up areas, which might also be the same as the volume. Finally, of course, and I showed this later on, you can even kind of increase this information with the building footprints nowadays, since we have a lot of building footprint data sets at the moment that were not there 5 years ago. Lately, we even made an improvement, so a WSF3D version 2, where we also included data from the Emporis data set. It's a point data set where you have per building information, so precise heights, because we knew from our first validations that we have particular problems with very high buildings, which in the SAR are not properly represented, and we could kind of improve this, let's say, knowledge gap there, and you can see it even in statistics. So with the first version, if you looked at cities, we had an average estimation error of minus 2.3 meters, so we underestimated by 2 meters, and now in average, one has to say, for a city, we come very close, it's just formally 22 centimeters. Of course, if you look at the absolute values, it's still of 3 to 4, 5 meters. Anyway, so just to show you, like, this is another view on the 90-meter data, and usually, of course, if you look at the small-scale structures within the built environment, 90 meters is quite coarse. But anyway, I show you on the left-hand side, for instance, we overlaid this 90-meter raster with a 12-meter WSF mask, and you can already then get a very precise idea of the building structure and the heights. And even here in this example of Munich, if you overlay it with OSM building footprints or Google footprints, it actually reflects quite well the build-up structure. Again, the footprints coming from another source, but then the average height in a 90-meter neighborhood still gives you a very good impression of the build-up structure that you can expect there. So using this data, what we did now with the colleagues from the World Bank and the George Washington University is calculating all kinds of statistics at the global level. So here on the left-hand side, you simply see the height distribution, so a histogram of the heights, for instance, for the UN macro regions. You can do it, of course, for countries, as you see here in the center, but also for single cities. And interestingly, then, if you are an economist or an urban planner, you can make use of this information. Of course, at first glance, you see that, for instance, in Africa, the average heights within the build-up area are rather low. So here we have a dominance of the bluish colors, whereas if you are in Asia, Europe, you see that there's also a significant amount of these reddish colors, meaning higher heights, so up to 10, 20 meters and higher. At the city level, it's the same. So here, the World Bank once called it a pancake city. It's like Lagos. It's comparably flat, so there are rather any or hardly any heights higher than 10 meters. But whereas if you look, for instance, at Seoul, you see that there's also a big component that just shows you buildings higher than 20 or even 30 or 40 meters. So all these kind of analyses are supported. Then, of course, what you see on the right-hand side, you can even start then calculating statistics on the country level. So here we see that's the distribution or the relation between the per capita and also with the average building height. And just as a general rule, of course, what you see is that usually the richer a country is, the higher are the average heights of the buildings that you can observe there. Also, of course, it's interesting to see if you separate the settlements, for instance, in the rural or towns. So these were settlements with lower than 50,000 inhabitants. You have cities with lower or between 50,000 and 10 million inhabitants, and megacities. You see that also there's a different distribution of the heights. Usually, the more urban you get, the higher are the average heights in your build-up or in your settlement. Same you can do if you take the volume, so it's a combination of the building footprint plus the height. And there we have a kind of a convex distribution where you can see, like, for the low income and low middle income countries, there's not really a clear tendency, but as soon as you come to the upper middle income and high income countries, you see that, again, there's this kind of rule of thumb that the richer you get, the more kind of building volume you have. And also there you see interesting differences between the countries. For instance, Germany is located here, it's above, so there we have comparably large volume per capita compared, for instance, to the US, and this also reflects that effects of densification, for instance, of sprawl, etc. Also, an interesting thing that the colleagues did from the World Bank is that if you analyze how the let's say how you differ the residual, let's say, from the mean. So, for instance, you can see if, like Saudi Arabia, if you are far away and below the average, it means that obviously compared to the other countries, let's say, in your income situation, here's the example of Saudi Arabia, you are with the building volume much below the average, which could be interpreted as that there's a high demand for volume needs. So you have comparably few volume per capita compared to your income situation. And this is now currently ongoing research where we look into the effects of if you really can derive, for instance, pressure on the housing market, etc., from these numbers. Of course, another thing that has currently been done is if you then take if you know these relations and you take the future projections of UN on the GDP, on the population, you might also start deriving with the average numbers that you have, trends or let's say demands for the future. So for instance here it's from 19 to 25 or even projections from 19 to 2015, and you really see depending on the current relationship how eventually the situation might be in the future or the demand, and this is of course important for policymakers and planners. This is a bit more complicated to explain. It's again based on the residuals. Here's an indication, let's say, if you look at the build-up area or the buildings in the background in gray, one can say that usually if you have outward growth, it's just one story. So it's the first story, whatever you have here in the height would mean that usually it's the plain settlement growth, but then or settlement situation, if you have more high rises or low rises and high rises, it means you also grow vertical. And this is, or you have a vertical dimension, a higher one. And if you compare this, you can then say, let's say, in this pro area, pro heights sector, if you are just relatively large proportion in your settlement or country is this up to one story height, then you would end up in this sector. If you are in these two here, you would end up more in this sector. And then if you have the high rise, we can even discriminate between 2.5 meters to 50 meters and higher than 50 meters. And this would correspond to these two sectors. So you see, for example, that Korea is even outside here, South Korea, I have to say, and means that it's pro heights. So there's a lot of, relatively a lot of high buildings. And if there are high buildings, they even tend to go high rise, so above 50 meters. The opposite is, for instance, Iraq. So you see usually most of the settlements have a dominance of the one-story buildings, and even if there are high rises, they tend to be comparably low. And again, this you can do for whatever spatial unit you are interested in. So here's another example where we went again for the UN macro regions, and it's interesting to see then where and how the distribution of these residuals are. And this, of course, gives you interesting information about the development patterns in 3D. And of course, finally, I want to conclude with an overview, let's say, or outlook, if you even zoom on or focus on single cities. So here's an example where we took from JRC's clusters database the city boundaries here in yellow. So this is New York, Beijing, and Munich. And then you can start, for instance, we have a procedure where we automatically define the city center and then construct concentric rings, for instance, of 500 meters or 1 kilometer. And then you can take the statistics, what's the average volume per ring, what's the average mean sum of the area, and then do all kinds of statistics and analysis within the city boundary. So this is an example from Paris. So we have these rings and also sectors. Then we have the statistics, what's the volume, the area within these. And then you can again start analyzing this. So here is one plot, one example for Accra, Lagos, Mexico City, and Paris, where we plot the height from the center, so the inner ring, to the outer rings. What is nicely to see is actually, let's say in plain words, here you go from poorer to rich, and you can see the richer a city usually, the higher are the building heights in the center, and also the higher is the ratio between the heights in the center and the outskirts. Another example is here, if you would plot per ring, let's say the average height, this is an example from New York, you can nicely see the midtown, let's say with the very high-rise buildings, and then even different other sub-centers, and this is also ongoing research where we test if one can use this, for instance, to identify polycentricity within settlements. Yes, and then also another colleague from the World Bank, Hogan Park, he looked into the relationship for a couple of urban clusters between the planning and zoning system, and if there's a correlation between the height and the building volume that you see. And in the first results, at least one can see that usually if there is a planning system, so here it's yes, then there are usually more heights. It's so going more up, so it means that also there, if you want to put it into a political message, it might be that you put more effort to densification, you want to avoid sprawl. That means usually if cities tend to grow, they go high. And also in other areas in the private sector, you see this tendency that if there is a more strict zoning and land use compliance and system, that usually it prefers to reduce a bit the sprawl and increase the height growth. Here with my almost last slide, I want to focus also your attention on another study that I did with colleagues, Karen Sito, who was also here. It lately was published. Here we used 5 to 10 kilometer scatterometer data and combined it with the WSF cross information. The scatterometer, in simple words, we analyzed the backscatter over time, and usually if you have more volume in the city, then also the backscatter increases. And we translated this into 2 and 3D crows. So the 2D crows came from the WSF over time, and the 3D crows came from the backscatter. And then you can start deriving these trends over time, which is, I think, the first 4D, let's say, cross modeling that you can have at a large scale. Although here, still the drawback is, of course, the spatial resolution. Yes, and with that, I'm done. Of course, you have seen this this morning in case and other presentations. There are a couple of other WSF data sets out there, and a few others will come in the next weeks and months. And we are happy with you if you want to use them. Also get in touch with us if you want to test them, those that are not out yet. And yeah, thank you for your attention.
Okay, thank you. Any question? Mic is coming.
Thank you very much, Thomas, for a very interesting presentation. My question is about, let's say, the 4 dimension that you just mentioned at the moment, with respect to what was done in the past using very coarse data set, I would say. And here, of course, the idea is in the future to do that. So, do you plan to have a 3D version of the world's footprint in terms of also different instant of time in the future, or you're just relying on the fact that, of course, other agencies are providing this data in time?
Yes, that's a good question. So yesterday I already discussed with Thomas Kemper that, of course, with this method we rely on digital elevation models which are available globally, which we know won't be, let's say, frequently updated at the global scale. So that was more like a one-time shot. And now we are already looking for methods like you use, for instance. Also, there are other publications out there that use deep learning models to kind of derive or estimate the heights from 2D satellite imagery like Sentinel-1, Sentinel-2. And I think that will be the future, because if you really want to come up with frequent updates of the height measurements, then you have to use 2D data, because the height models are not available frequently enough and also not in the global coverage. But at least from our side, it's still a long way to go. It comes to a stable estimation, at least, of the heights.
Yeah, maybe I'm adding to that. So this is really a pledge to the people interested here in this topic here in this group. There's a big demand for coming up with methods that are scalable globally and repeatable. So there might then be even funding on the Copernicus side, because we need to go into this 3D global monitoring. So if you have ideas, go ahead there, and we'll be happy to support you.
Okay, let's thank again our speaker. Let's move to the other one.
I now invite on stage Ritu Java from KTH in Sweden. And she will be talking about unveiling 3D insight of buildings from multimodal Sentinel-1 and 2 time series. How is yours? Go ahead.
Thank you, Nicola, for the introduction. I will be talking about building height estimation using Sentinel-1, Sentinel-2 time series data. So how do we measure building height using satellite image time series data? The first thing is we have an example over here from Sentinel-2. It's in Rotterdam. So if you can see, there are shadows close to the buildings. So that is one of the major feature we need to measure building height. And when it comes to time series, so over time, the shadows changes from one season to another season. Right now we have an example from summer to winter, but we can see more changes when we track like monthly and also over different seasons as well. One is shadow, and then there are other seasonal changes. when I'm saying seasonal changes, it's mainly in the surrounding. So we can also track the constant factor and the variable factor. So variables would be in the surroundings, and the constants are mainly buildings. Then we also use Sentinel-1 data. So we know that Sentinel-1 SAR is also highly correlated with building heights, but there are issues like overlay and shadowing, and then also the double bounce and all those things. We have those issues with Sentinel-1, but to deal with them in a better way, we use both ascending and descending images. And here is an example from, it's again the same example from Rotterdam. Ascending orbit and descending orbit. So there's a bit of angular change, and you see there's similarly there's a change in the backscatter information here. Now next is the urban mapping from 2D to 3D layer. So what are the applications of 3D building height estimations? I think our audience is very well aware of the applications now. So energy consumption, urban heat island, population distribution, population estimation, and also disaster impact analysis, and all over, if we combine them into one, then it's urban sustainable development. Now at small scale, we have a lot of studies which are available at high resolution as well as low resolution. At large scale, we have mainly two global solutions. One is WSF from DLR, WSF 3D, and then we have one from JRC, GHSL building height products. Now WSF is at 90-meter resolution, and GRC provided building heights at 100-meter resolution. Now with this, our objective is to do large-scale building height estimation. We don't want to stay to a small scale, like city scale, even at country scale. We want to expand to multiple countries and eventually to global scale. And then to improve resolution. As of now, the global products are at 90-meter and 100-meter. Here we are targeting 10-meter resolution, and maybe in future, even better. Then the third point is we just want to use open source data. So we are here relying on Sentinel-1 and Sentinel-2. So that, and the main point is, if we have global data, we can expand the application to global scale. Then on the right-hand side, we already have our preprint. So, and now our data set. So our study area is basically all over these 4 countries, Netherlands, Switzerland, Estonia, parts of Germany. And then we also have our test set in 10 other European cities like Madrid, Stockholm, Warsaw, Nice, and in total 10 cities. In total, we have 60K urban data points, where one data point is of size 1280 meters by 1280. Our building height references are at 10 meters spatial resolution, and these ground truths come from the land and administration offices of these countries, like Swiss Topo, Estonian Land Board administration offices. So they are pretty much called gold standard. Then our input is Sentinel-1 SAR time series, and when we are talking about time series, it's 12-month time series. So 1 image per month. So basically 1 best image per month. When it's Sentinel-2, so least cloudy image per month. So we use Sentinel-1 SAR and Sentinel-2 multispectral images, time series data, and on the left-hand side bottom, we also show the distribution of our data set. So the first one is the distribution of entire data set, which is training and testing. And then we show like distribution on each country, each of the 4 countries. And then the last one is our out of distribution, out of distribution test set. So if we see the mean height and the standard deviation in the first 3, 4, 5 is around 4.5 meters and 3.8 meters, whereas in if we look at our out of distribution data set, The mean height is around 8 meter, and the standard deviation is around 9 meter. So it's actually out of distribution data set. And this is going to be our second test set. First test set is in distribution, which is holdout data set from these 4 countries. And then the second one is the out of distribution test, which is from these 10 European cities. Then this is our network architecture, where we combine basically, it's an encoder-decoder type of architecture, where the encoder consists of shared convolution neural network combined with SWIN transformer, because they are like strong feature extractor, both globally and locally. And then the decoder is a standard decoder, but there are some architectural tweaks here. And then we, to take the advantage of the temporal dimension, we use temporal attention module, which is LTAE. You can find these references in our preprint. Sorry about the technical details. Then we have our results on the right-hand side. So with this model, we get around 1.89 meters of RMSE. And our R square is around 0.58, in fact 0.5, sorry, it should be 0.53. No. Yeah, I can say. So our R square is around 0.54 and IOU is 0.59. And then we show our ablation study to basically show the advantage of different architectures, architecture choice, like why we use different, the consistency loss, why we use multitask learning, and then we also compare with what if we just use one image and what if we use entire time series, and then we also show the difference between just using the SAR data and just using the optical data. And then we test it, as I already mentioned, we have 2 test sets, in distribution and out of distribution test set. So the last table, the third table, is about that. So generalization is basically testing on the out of distribution test set. So on in distribution test set, we have around 1.89 meters of RSE on our building heights. But when we go to out of distribution test set, it becomes around 3.2 meters, so around 3 meters. So we see, we already see that there is a drop in performance, but it's not huge. 3 meters is around 1 floor of height. And also in R square, we see a drop, again, 0.54 to 0.48, which is, again, if we see the results later on, it's not that much, but yeah, we still need to improve in that direction. Then we also estimate building height on pixel basis as well as instance basis, because instance-wise building height estimation is more interpretable, it's more usable. So at pixel, our RMSE is 1.89 meters square on in-distribution data set. But if we do instance-wise estimation, it becomes 1.60, which is lower error, so better results. And here are some of the samples from in-distribution data set, one from each country, Netherlands, Switzerland, Estonia, and Germany. It's also high urban area and also some sparse areas. So yeah, we have Sentinel-1 image, Sentinel-2 image, and then reference, and then our prediction, and then the last one is the segmentation. So we see building or no building, and then we also see the corresponding heights. Then we have an example from each of the test sites. So these are all 10 sets, test sites. And here we can see the generalizability results, that the ground truth and our predictions are pretty close. So yeah, even though we see a higher error around 3.2 meters, it doesn't seem to be that bad. Then we have instant level visualization. So we convert from pixel level results to instance level results. To convert that, we use building polygons, building footprints, and we use 70 percentile of height. And with that, we see the results are already improved. So 1.89 meter to 1.60 meter of RMSE. And this is an example from Winterthur city from Switzerland. So we can, yeah, you can see the results are pretty good here. Then we also have a Google Earth Engine app, so you can basically visualize all these data on Google Earth Engine, zoom in, zoom out, and check, and also compare visually as well as with the ground truth. This one is an example from a city in Netherlands. Then we also present results at 100-meter resolution. So till now we were talking about 10-meter resolution. Now, since we know that there is a really good product, global product available at 100-meter resolution, so we convert our 10-meter results to 100-meter results, and then compare with the GHSL product. And here you can see some comparison, both in terms of samples as well as correlation, and also in the table. If you see the RMSE difference, we are getting an RMSE of 0.3 meter, whereas from GHSL we have 0.56, and similarly there's a huge difference in R square. And the R square can also be visualized from the correlation diagram. If you see the right correlation diagram, it's really scattered, whereas the first one from us, it's really aligned with the diagonal, which says that our building predictions are highly correlated, not perfect, but yeah, better correlated with reference. Now with that, if I want to conclude, then we have building height prediction at 1.89 meters of RMSE. We are doing large-scale building height estimation with improved spatial resolution, with improved accuracy both at 10-meter and 100-meter. And we are using globally available Sentinel-1, Sentinel-2 time series data. That means and as of now, we are generalizing it within Europe. But if we are using globally available Sentinel data, we can also extend it to different continents. Now we also have our GitHub repository over here. If you want, if you want to connect and get our future updates from our upcoming works, maybe in next few months. Next month, actually, there is an uncertainty aware building height estimation product. And then we are planning to embed super resolution with this, so that we can also improve from 10 meters to 2-meter spatial resolution. And our main goal is basically to improve the scale. Currently, we are in Europe, so we want to extend further. So we are looking for more data. So yes, if anyone of you know a few sources, it would be nice to connect. And that's it from my side. Thank you so much.
Great presentation, thanks. Any question for Ritu? Please.
Thank you very much for your presentation. So one question, which is a general question that maybe is not directly to you, but also to the other people that were discussing about 3D first. So when you're talking about super resolution, I guess it's basically that you would like to have the height of the building, let's say, at 1 meter spatial resolution, which means that you are getting, let's say, smaller object on top of the buildings as opposed to the main, let's say, floor of the building. Or you are able to get something which is, let's say, not a flat roof exactly along the differences. So my point is not the question is not to you. Is it useful? I mean, do we really need to have information? I mean, this is a question also to the next speaker, which is my PhD student. So you know, I mean, it's basically so these approaches which are based on pixel-based height extraction as opposed to building-based height extraction, which is the mean or the maximum or whatever. That's a big question I mean, it's not a big question in terms of the methodology, which I understand. It's much better to have an algorithm that works better and so on and so forth. But for global analysis, maybe it's shooting to a small mouse with a big gun. It's more a comment than a question, sorry.
So your question is to basically do building-wise estimation rather than pixel-wise estimation? Yeah. So we can create instances from our pixel-wise estimations. So here we are filtering or post-processing our results using building footprints or building polygons, but it's not necessary to take this route. We can also convert, we can also create vectors or polygons from pixel-wise results as well. So we don't really, we don't have to rely on building footprints polygons, but since they are already available, and at least in Europe, the coverage is pretty good, and I agree they might not be updated frequently, but the coverage is good, that's why we are using it. But yes, having said that, in future, yeah, we would be doing, converting it into LOD models directly from the pixel-wise estimations. And coming directly to the instance-wise building height estimation, that means we need to take an object-wise approach rather than pixel-wise approach. This already exists, I think, for high-resolution images, but not so much with Sentinel, but it would be interesting to look at it, how accurate or if at all it is possible or not.
Okay, any other question? Please.
First of all, also thanks for this very nice presentation. Could you also, in your validation, take a look at the estimation errors depending on the height? Because that's what we saw. Like usually, of course, the low-rise buildings are quite accurately estimated, but the higher it gets, the larger is the error as well.
Yes. So we did an evaluation both in distribution and out of distribution by categorizing building heights into different categories. Yes, you're perfectly right over there. For short buildings or medium level height buildings, they are mostly accurate, but for taller buildings, and in our case, greater than 30 meters of height, we saw that there's like increase in error. So yes, and that is one of the reasons we think super resolution might help. We already have like initial level of results with us, and we can see up to, with super resolution, we can get better accuracy up to 50 meters of height. So that is already doing a lot. So, but in future, yeah, we want to improve more.
Thank you.
Thank you so much for your question.
Thanks. I guess we have to... Okay, let's go. Go ahead.
Just a quick question. When you calculate the metrics, are the metrics related only to buildings or you compute also the zero values that are at the ground? Because it will totally
biased.
differ. Yeah.
Yeah. No, they are only on the foreground pixels, so only on buildings.
Okay, so use some mask, to compute the metrics or the segmentation mask. Okay, perfect. Cool.
We don't need to actually use the masking or from segmentation. Yeah, we already have the ground truths, right? So it's already masked. Yeah.
Thanks. It's time to move to the next speaker. Thanks a lot.
Okay. Thank you so much.
Okay, so I'll invite the next speaker, Luigi Russo from University of Bahia and University of Sannio. He will talk about deep learning system for automatic extraction of 3D building heights on large scale using very high resolution Cosmos KML data. The floor is yours.
Okay, so good afternoon to everyone. I am Luigi Russo, a PhD student from University of Pavia, and today I'm honored to present the following work, which is a collaborative effort involving also my two PhD supervisors, Professor Paolo Gamba from Unipavia as well, and Professor Silvia Ullo from University of Sannio. So we know that, and this has been a constant concept throughout this whole session, that accurate 3D building data are crucial, let's say, for urban analysis and also for the assessment of disaster outcomes. So for modeling, for example, the let's say hazards like floods or earthquakes. And this work is in line with, in particular, with the Sustainable Development Goal number 11 for inclusive, safe, resilient and sustainable cities, and moreover, it also aligns with many global disaster risk reduction frameworks. So moving on to the analytical aspect, well, how is this problem typically treated? We have seen that this is a regression problem. We were discussing about this. So there are many references through the state of the art which treat this problem like a regression task. And most of them are using high but not very high spatial resolution satellite data, with often the combined use of optical and SAR imagery, which can be combined in many different ways. So this work instead relies only on very high resolution satellite data and specifically utilizes only pure radar information provided by Cosmos Skymed imagery. So how, in this case, is this problem, let's say, assessed? We are using a UNet model, which is a popular computer vision framework, whose let's say, which is enhanced by the integration in different points of the network. Integration of an attention mechanism, whose configuration is shown here in the right of the slide. Well, this block helps the model to focus only on relevant parts of the data, and in particular, this indeed improves the extraction of building heights from image backscattering data. So the overall workflow of the methodology which has been used is shown here in this slide. In particular, the input Cosmos Skymed sequence patches are fed inside the attention unit, and we use as output to the model, deep learning model, we use a simple ReLU activation function which helps to speed up the, let's say, the convergence, the training process, the convergence process, because it outputs non-negative values, which are, I mean, the regressed value for the building heights that of course are non-negative, and they are the prediction are iteratively compared to the ground truth during the training, which is represented by a combination of the digital surface model and digital terrain model, which form the normalized digital surface model that represent all the objects above the terrain, and to exclude all the non-building objects, it has been performed a pixel-wise multiplication with the binary footprint masks from OpenStreetMap. So this generates the ground truth. In particular, as training, let's say, as training site, we considered a Cosmos Skymed imagery street map image acquisition mode, whose configuration is shown here, is detailed in the slide, representing the entire metropolitan area of Milan City, to generate the training and also validation sequences. It has been performed a division of the whole tile into smaller chips with an overlapping stride to augment the total number of training samples. Moreover, to assess the generalization capabilities of the model, it has been considered three different test sites represented by three different cities not so far from Milano. They are Pavia, Sant'Angelo Lodigiano, and Lodi, and among them there is no shared spatial domain. So this means that the model, these are, let's say, data that the model, I mean domains that the model has never seen throughout training, so has never updated its weights on these particular areas. So moving on to the results, here we show on the right, qualitatively speaking, the predictions on validation set for Milano City, in which we also considered, with respect to the reference one used for training, other two Cosmos Skymed imagery with images with same satellite, same orbit with respect to the reference one, but with different step acquisitions going progressively ahead in time. And as you can see, there is a graceful degradation of the system over time because the error, which has been evaluating, the evaluated error, which is the RMSC, which has been evaluated both outside the buildings, it means on the areas that are supposed not to be buildings, to quantify the ability to identify the urban areas and also the error of buildings on the building pixels to quantify the accuracy instead. In the regression task is increasing over time. So while these are similar outcomes for the test sites, as you can see, we are going to discuss in the next few slides in detail the error. What you can see on the right is that the predictions are noisier. Basically, this is related to the fact that the model has never been, let's say, this is a new domain, new spatial domain, which the model has, let's say, never seen. So as regards the error, as you can see in these histograms, we reported the height, distribution of heights for the different sites. As you can see, there is a higher RMSC for Milano City, even though part of this area has been used for training the model. And this is basically, if you see the distribution, this is due to taller buildings in general and greater height variability, while instead for the other test areas, there is overall lower RMSC, and this is because the distribution are, let's say, narrow, and also, let's say, there are in general lower buildings, and this, of course, the model in this case, this leads to more accurate predictions in general, and this is also, let's say, justified by these scattergrams, in which there is a general underestimation trend of the building height with respect to the ground truth reference height. As you can see here, there is a linear relationship between the absolute error and the ground truth reference height, and this quantifies the, let's say, the degradation of performances of the model, assesses the degradation of performance of the model with increasing of the building height. So to conclude with this work, we want to present, let's say, a starting point of a deep learning-based methodology for the height estimation, three-dimensional height estimation of buildings on large scale. And to do this, we rely only on very resolution Cosmos Skymed radar data, and this has a great benefit when evaluating, for example, emergency responses and also disaster outcomes. There is a very good performance in regressing buildings with moderate heights, while there is room for improvement when going in the prediction of taller building structures. So as future direction, we will go, into this latter aspect. So, for example, exploring domain adaptation techniques, so utilizing techniques like transfer learning and fine-tuning to improve the overall model generalization across different regions, and also including external information inside the model to, let's say, to improve overall the outcomes. So these are the references considered for the given study. Thank you very much to all of you for your attention.
Okay, are there any questions? Okay, if not, I can start. Today the audience is a bit shy. So, can you talk more about the generalization capabilities of your model?
Yes, I mean, what we previously discussed is related to the fact that, let's say, and this is something that you can see here, there is more noise in the prediction when, I mean, evaluating prediction on the test areas. And I mean, this noise, when you check the comparison with the ground truth, is related to the fact that, I mean, properties in the images, Cosmos climate imageries are, let's say, changing, backscattering properties. This is something that you can see, and is also, let's say, motivated to the fact that, for example, the acquisition dates for the images in the test area are different from the reference one on Milano area utilized for training. So there are changes also within the overall image, and basically this is something that can be, let's say, in next works can be improved by, for example, utilizing a data set which is including different areas, and let's say also exploring transfer learning and fine-tuning techniques can be of help in this case.
Okay, thanks. You already replied to the second question, so
yes.
You are planning to expand your dataset, right?
Yes. That's what we want to do. As my colleague said previously, Babak said, we have access, I mean, to Cosmos climate imagery, and so we do not have constraint and limitation on the download of the data. Now, since we are dealing with very high resolution images, I mean, this can be also expanding your data set by including, for example, two or three cities can improve the outcomes. So this is something that we will do.
Thank you. Other question? Okay, if not, let's move on because we're running a bit late. Thank you.
Thank you.
So I invite on stage the next speaker, Johan Stur from CS Group, and he'll give a talk on generating semantised 3D meshes with cars, a scalable open source multi-view stereo framework. Please.
Good afternoon. So my name is Johan, and I work for CS Group. So I will talk about generating 3D meshes with cars. So what we want is to generate 3D meshes that are semantised and from sensor images and be able to manipulate them afterward. So first, we need to generate point clouds, semantised point clouds. To do so, we will use cars. So we'll talk a bit about cars. It's an open source satellite multi-view stereo framework. It's developed for the CO3D mission by CS Group for the French Space Agency. It generates digital surface models from high-resolution sensor images like Pleiades, Pleiades Neo, Spot, CO3D, WorldView. And to this input sensor images, you can add layers, for example, the associated color, the classification. Imagine you have a neural network that classifies your images. Well, you can use it in cars. So to simplify a bit, cars is composed of 4 main steps. There is resampling step, matching, triangulation, virtualization. First, we generate epipolar images. So that means that is for a left image, so we work with a pair. For the left image, for each pixel, the corresponding pixel we want to find is on the same line than the pixel on the left. So then we generate a disparity map with Penrose, which is also an open source tool for a CNES open source tool for stereo matching. So we have the displacement map from left to right, and then we can transform it to elevation map. So we have the X, Y, and the 8. So we do it with Sherlock, which is also open source. And you can also have a LAS file. Then, when you have your point cloud, you can rasterize it. So here you have your DSM. In every step I showed, you have the classification you have put in input. So your point cloud is semantized. So it's only information, but you can also use it in the pipeline. So you might ask why you want to use it in the pipeline. Well, for example, in Penrose, well, we do some errors because correction is not a simple task. So you can add constraints to avoid correction errors. So, for example, you don't want to match a left pixel corresponding to a tree to a right pixel corresponding to a building. So you can say you don't want it in your machine. So, for example, we add constraint in a semi-global matching algorithm in Penrose, and we obtain better results. So to summarize a bit, CARS is open source. So it's open to contribution. It's scalable. So CARS can run entire triad, for example, on your laptop or on an HPC. And it's modular. So everything can be plugged to CARS. Imagine you have sensor images with geomodels that are not supported by Sherlock. You can create your own geometry plugin, plug it into CARS, and CARS is available for your sensor images. You can plug in application. So imagine you want to add a denoising application for point cloud. Well, you can add it if you are not happy with the current version or method in the rasterization step in CARS, you can change it. And also you can add a new pipeline. So now we have our semantized point clouds, and we want mesh, semantized mesh. So to do so, we'll create a new pipeline. So we want to extend CARS, so we create a plugin that will generate meshes. The objective is to generate level of detail 2 meshes on urban area, principally on building, that are semantized, robust to outliers, and we want for each point to use the confidence of the point and information we have inside CARS, and the classification of each point. So we have this plugin available on GitHub too. So in the method, we strongly use the classification of building in the processing. And as it extends from CARS, it's highly scalable. So you can run the mesh process for an entire period. A little demonstration on Toulouse. So we generated the mesh on Toulouse with the plugin. So you have a few classes like building, vegetation, water, and we added the roof class. And of course, you have the texture that is generated from the color images. All from in this example, from pre-add images. So now we have meshes, and we want to visualize it. Well, you just did. With a demonstrator we created to challenge a bit our meshes. So the demonstrator is based on Cesium. So it was created to use custom visualization of our meshes, to modify textures, to merge it with OpenStreetMap data, to also do some simulation, because we wanted to challenge it. So, for example, we tested flooding simulation on it, and you can have real-time interaction with the meshes from the user. So you can use whatever you want as a visualization tool, but we'll talk about another one, DT Insight. So it takes as input everything we have seen, so 3D tiles, DTM, meshes, point clouds. It's converted to 3D tiles, and the data is streamable. So with this tool, for example, developed by CS Group, you can go on the website, load your data, and you can manipulate it in the web browser. The data is like a few giga. And of course, you can manipulate the classification inside it. You can have access to OpenStreetMap data directly with a mesh. Everything you want. So we started from stereo images with classification. With cars, we created semantized point cloud. Then we created with a plugin the semantized meshes. We could have done a full pipeline going from stereo images to meshes, and then we visualized it. Do you have any questions?
Any question about cars? Yeah, please.
Thank you for the presentation. I'm a little bit confused with when you mentioned classification is included in every stage. Is it included as an input
yes,
to each bezel, or is it classified automatically?
Yeah, you have to add it as input, but we also have internal plugins that classify automatically, for example, epipolar images in Pandora. But for cars, you have to put it as input for now. So it has to be pixel to pixel accurate with the sensor image.
Yeah, thank you.
Very short question, please. We are very late.
Yeah, thank you. Well, as a practical question, if I would like to process the small city, like Toulouse, can I do that with my laptop, or do I need like a...
Yes, you can use your laptop. It might take some time, like a few hours, but it will run.
Okay, great, thank you.
To generate DSMs as much as meshes.
Thank you.
Okay, thank you very much again.
Okay, I'll invite the last speaker, Maria Golemi from Remote Sensing Lab Foundation for Research and Technology, Hellas in Greece. She will talk about 3D surface temperature modeling evaluation with in-situ thermal remote sensing, a study in Berlin. The floor is yours.
So, hello everyone. I'll try to make it quick because we're late. Hi, I'm Maria, and I'm going to talk to you about a very small part of what we do in the URBIS24 project, which is an ERC-funded project that you've probably heard about in a couple of talks before this one. So we all know the importance of surface temperature in cities. I won't elaborate on that. And we also know that satellites cannot capture the vertical component of cities in a fine scale or accurately, and they must be complemented by in situ thermal infrared observations and modeling. So one of our goals in this project is to use this modeling to assess the complete temperature from satellite thermal observations, and the goal of this particular study is to evaluate 3D surface temperature that is modeled against in situ thermal infrared observations. So the model that we decided to use is called VTAF3D. It's a mix between TAF3D, which is a well-known model by Krajinhoff and Vogt, and MEISPA, which is a model that models several vegetation processes, such as radiation absorption, photosynthesis, etc. And essentially what it does is it calculates energy balances and also surface temperature in 3D in a very fine scale. Our study area is in a suburban area in the southeast of Berlin, and if we zoom in, you can see where it is. This is a close-up from Google, and you can see that characteristic very tall building in the middle of the area. And there we have mounted 4 thermal cameras that we're going to use for the evaluation of the model, and they're overlooking the area below. So 1, 2, 3, and 4 cameras, and you see the fields of view. And we also have a meteorological station that provides us with the forcing data for our model. Things such as incoming radiation, shortwave and longwave, air temperature, etc. And this data was gathered in August 2022. So to parameterize the model, we need to get some thermal properties for the buildings, and for this we used the Tabula database. We matched the buildings in our study area as best as we could with buildings in the database, and then we used the structure that we obtained for the walls and the roofs to get the thermal conductivity and the heat capacity from the CISBE guide, which is basically a guide that provides a lot of material properties. We also used Earth observation data to parameterize the model, so NDSM and also land cover. It was in a very fine resolution, and to basically make sure that we could model the area, we upscaled to a 5-meter resolution, and also we cut smaller pieces of our domain. So for each camera, we conducted a different simulation. So we have 1, 2, 3, and 4 different simulations. And for time economy purposes, I'm going to talk about 2 areas, this one and this one, so top left and bottom right. So here you see the top left. Here you see the NDSM after we upscaled it to a 5-meter resolution. In the middle, you see a snapshot of a 3D surface temperature that we simulated. And in the right, you see the surface temperature from the thermal camera. And what we did to compare the two was basically take a surface that was well observed in both the simulation and the camera, and take the average temperature time series for the whole simulation period. So for example, you have this wall, which is observed here and right here, and we take the average temperature. In the diagram in the bottom, you see in green the simulated surface temperature. The blue line is the average surface temperature from the camera, and we also have the whole temperature bandwidth from the camera, which is quite wide. We take several areas. This is one wall, and the second is this roof, for example, and we see that the patterns match up quite well, although, for example, here we have some overestimation during the day when you compare the average temperatures, and some underestimation during the night. So here are the error metrics, and we see that the mean absolute error over the whole time series is 4.3 degrees for the wall and almost 8 degrees for the roof. This is the other area, and again, we do the same. We take one area, for example, this roof right here in the middle of the site, and we see that the patterns match really well, except for some underestimation of the surface temperature during the night. Another wall, again, the patterns match really well, but we have some underestimation of the model compared to the camera. At worst, this is 5 degrees. Most of the time, it's less than that. And then lastly, this wall right here in the right. Again, we have good matching, except for these spikes, which we have several hypotheses to where we can attribute them, but we are not yet concluded in that. Here you see the error metrics, and again, for the most part, they're less than 5 degrees. We have 3.8 for one wall, 2.76 for the other wall, and 5.14 for the roof. So, to conclude, we know that the model has several limitations. For example, it considers that all roofs are made of the same material and have the same properties. The same goes for walls, and the same goes for streets. Also, it assumes periodic boundary conditions, which means in domains that are not really uniform, such as the one we had here, you can have weird stuff happening at the edge of your simulation domain. It was also surprisingly hard to identify the buildings and specify the material parameters really accurately. And overall, however, the model has quite acceptable performance, and maybe we can fine-tune it even further. The model temperatures will be used in analysis of urban surface temperatures, combining in situ, airborne, and satellite remote sensors. And we also have a poster about this, but seeing as this is the last talk of the conference, maybe you can't catch it. But yeah, maybe you want to. So that's all from me. Thank you.
Thank you. Okay, are there any questions? Please.
Thank you, Maria, for this very nice presentation, and I believe that is a real advancement of how we should interpret observations. Huh? So my question is about the thermal camera that you were using for ground validation. How did you calibrate that camera, or it comes from the calibration from the factory, or does that work?
So I wasn't the one who calibrated or mounted the cameras. I think they were calibrated because we have one same camera that we use in the lab in different things, but they come ready to use as far as I'm aware.
Okay. And this camera is like is refrigerated, or is just without cooling?
I'm not really the
Because
cameras in itself is not cooled, but obviously
okay.
you can have custom-made box to protect it, and you can incorporate cooling as well.
Okay. Thank you. Congratulations, Maria.
Other questions? Maybe a curiosity on my side. How easy is to scale this product?
So the model has, as it works in 3 dimensions, you have to take all 3 dimensions into account. So for example, this tall building was a hindrance in our simulations because it's approximately 80 meters tall. So you have 80 meters tall in your simulation. But if you don't take it into account, you can obviously expand in the X and Y directions quite a lot. It also depends on the resolution that you're using. 5 meters, I'm confident that you can expand about 100 meters to each direction, but not really much more than that.
Mm-hmm. Okay. Thank you. So I guess we can
yeah.
session here.
So
let's thank again the speaker.
So it's time to move to the big hall, and then the wrap-up session will start, I guess, in the coming minutes. Yeah, I sent it to Sabrina, so she will already get it. Well, there was some time.